Hello there, and welcome to Physics with William, where curiosity gets comfortable and science takes its time. Tonight, we are settling in with a topic so small that it almost refuses to behave like an ordinary idea at all. We are going to spend some time with Planck time, often described as the smallest meaningful unit of time in modern physics, though as we will see, even saying it that way opens up more questions than it answers. It is a concept so tiny that if a second were stretched into something vast and familiar, Planck time would still be hidden far beyond anything the mind can picture in everyday life. It is not just a very short moment, it is a threshold where our usual understanding of reality begins to lose its footing a little, which is always an encouraging sign if you enjoy physics and are not too attached to common sense. Before we wander too far into the deep end, I would love to know where in the world you are listening from tonight, and what time it is in your little corner of it. It feels fitting, does it not? A quiet discussion about the smallest possible sliver of time, while each of us sits somewhere under a different sky, looking at a different clock, arriving here by way of our own long day. And if you find this soothing, interesting, or simply a pleasant way to unwind while your brain gradually stops trying to organise tomorrow, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this gentle corner of science find other people who might also enjoy drifting off while thinking about the structure of the universe. Now, I should warn you at the outset that Planck time is not one of those scientific ideas that slips neatly into the mind and settles there politely. It is more the kind of idea that knocks on the door, comes in uninvited, and starts moving the furniture around. At first glance, it sounds simple enough. Perhaps time, like a loaf of bread, can only be sliced so far before you reach the smallest sensible piece. Perhaps there is some final tick beneath all the other ticks, some ultimate beat too small to divide further. That is a very natural way to think about it. We spend our lives measuring time by units nested inside larger units. Seconds inside minutes, minutes inside hours, hours inside days. Even when we go smaller, we remain comfortable. We talk about fractions of a second. We talk about split seconds, brief moments, instants. Our language is full of ways to shave time thinner and thinner, as if with enough patience and a sharp enough knife we could keep going forever. Physics, however, tends to become a little suspicious when human intuition gets too confident. That suspicion is often justified. The world is under no obligation to be arranged in a way that feels convenient to creatures who misplace their keys and still struggle to fold fitted sheets. So when physicists speak of Planck time, they are not simply offering a very tiny duration for the sake of showing off. They are pointing toward a scale where our current descriptions of nature begin to fail in a very particular way. That is important, because Planck time is not just small. Smallness by itself is not especially mysterious. A grain of dust is small, a cell is small, an atom is smaller, a proton is smaller still. Physics has spent a great deal of effort descending these ladders of scale, but Planck time belongs to a stranger category. It marks a boundary where the frameworks we rely on to talk about time, space, energy, and gravity all begin crowding into one another so tightly that our best theories stop cooperating. To understand why that is so fascinating, it helps to begin with the ordinary experience of time, because ordinary experience is exactly what breaks down here. In daily life, time feels smooth. It feels continuous. It flows, or seems to flow, in a way that does not come in visible chunks. You do not wake up and experience the morning as a sequence of separate time pellets being dispensed one by one. You experience continuity. The kettle takes a while. The tea cools slowly. A conversation drifts along. Traffic lights remain red just long enough to make philosophical despair seem reasonable. Even when we use clocks, the measurements feel like markers laid onto an already existing stream. The clock is not making time happen. It is merely helping us count its passage. That impression has deep roots. For a very long time, people thought of time as something universal and steady, almost like a grand invisible background against which everything else took place. Even after physics became much more sophisticated, everyday experience continued to support that feeling. Time seemed smooth enough for mechanics, engineering, astronomy, and ordinary life. If you threw a ball, baked bread, planted crops, or scheduled a train, you did not need to worry that time might become fuzzy or grainy at extremely tiny scales. It was simply there, dependable and uninterested in your opinions. Then modern physics complicated the picture in several stages, which is one of its favourite hobbies. First came relativity, showing that time is not the same for everyone. It stretches and shifts depending on motion and gravity. That alone was enough to upset the neat old idea of a single universal clock ticking identically everywhere. Then quantum theory arrived and made the microscopic world behave in ways that seemed less like tiny clockwork and more like reality, improvising under pressure. Suddenly, the very small was no longer just a scaled-down version of the familiar. It was a place where certainty gave way to probability, where particles behaved like waves, and where measuring something could alter the outcome. Those two great theories, relativity and quantum mechanics, are both extraordinarily successful within their domains. Relativity describes gravity, motion, space, and time on large scales with astonishing power. Quantum theory describes the microscopic world with equal brilliance. The trouble begins when you try to make them speak the same language in the most extreme circumstances, and Planck time lives right in that trouble. It is named after Max Planck, one of the founding figures of quantum theory, though I suspect even he might raise an eyebrow at how often his name now gets attached to scales so extreme they sound like science fiction, trying to impress its friends. Planck was the physicist who first introduced the idea that energy came in discrete packets, a move that helped open the door to the quantum world. Later, certain natural scales were built from the deepest constants of physics and named in his honour. Among them was Planck time, a duration so brief that it sits at the edge of meaningful physical description, at least according to our current understanding. And this is where one must be careful. When people hear the phrase smallest unit of time, they often imagine something like a smallest pixel on a screen. They imagine that the universe updates in little jumps, one Planck time after another, as though reality were a sort of cosmic slideshow with very good production values. That is not what physics confidently says. It's a common interpretation and a tempting one. But Planck time is not established as a proven indivisible atom of time in the way a second is a unit on a clock. Rather, it is the scale at which our existing theories can no longer be trusted to describe time in the ordinary way. That distinction matters. Planck time may be a true minimum, or it may simply be a warning sign saying that our concepts stop working beyond this point, which in physics is often even more interesting. Imagine trying to describe the surface of the sea during a storm using only the language of calm ripples in a pond. Your words might work reasonably well up to a point. You could describe waves, motion, surfaces, reflections. But eventually the storm becomes too violent, the scales too chaotic, and your pond language breaks apart. That does not mean the sea has ceased to exist. It means your model has reached its limit. Planck time is a bit like that. It may tell us something fundamental about the grain of reality, or it may tell us that we are bringing the wrong tools to the most violent, compressed early moments of the universe. Now, one of the reasons this idea captures the imagination so easily is that it places us at a conceptual edge. Human beings are very drawn to edges. We like borders, first moments, last moments, smallest things, largest things, final ingredients, ultimate answers. We like to know whether there is a bottom floor or just more stairs. Planck time offers exactly that sort of temptation. It seems to whisper that perhaps time itself has a basement. Perhaps you cannot keep slicing forever. Perhaps beneath everything we know, beneath every heartbeat and orbit and decay and oscillation, there is a smallest possible interval, too tiny for the universe to subdivide. But then the questions begin arriving in groups. If Planck time is the smallest unit of time, what would it even mean for something to happen within it? Can there be before and after inside the smallest possible before and after? Could a clock ever measure it? Could anything physically change over such an interval? Is time made of little pieces, or is Planck time merely the place where our theories throw up their hands and ask for reinforcements? And perhaps most unsettling of all, if there is a smallest meaningful interval, what does that say about continuity, motion, causation, and the smooth passage of time we seem to inhabit so comfortably? There is also a deeper emotional appeal here, though physics rarely writes that on the label. Planck time takes something utterly familiar, time itself, and reveals that at the smallest imaginable scales it becomes almost unrecognizable. That is always a powerful scientific move. We begin with what feels obvious and end with something strange. Light seems straightforward until it behaves like both wave and particle. Matter seems solid until it turns out to be mostly emptiness and fields. Time seems continuous until physics hints that continuity may not survive all the way down. These shifts are unsettling, but they are also part of what makes science so compelling. It keeps reminding us that reality is not only larger than we suppose, it is also structured differently than we suppose. Consider how often time governs our lives without our permission. We schedule by it, age by it, remember by it, worry by it. It is the medium through which every human story unfolds. We talk about saving time, wasting time, making time, losing track of time. We act as though it were a resource and a setting and a force all at once. Yet when physics approaches its deepest limits, time stops behaving like a simple background. It becomes tangled with energy and gravity and uncertainty. It becomes a participant rather than a passive stage. And at the Planck scale, it may not even retain the smooth identity we're used to giving it. If all of this sounds slightly unreasonable for a quiet evening, that is because it is. But it is the good kind of unreasonable, the kind that stretches the mind just enough to make the ordinary world look a little more interesting afterward. Once you start thinking about Planck time, even the second hand on a clock begins to seem rather grand and leisurely. A second is no longer merely a second. It is an enormous expanse compared with the scales at which the deepest questions of physics begin to stir. Every blink becomes a kind of continent of duration. Every pause in speech becomes absurdly spacious. It is one of the few topics capable of making daily impatience seem mathematically theatrical. The next time someone says they will be ready in just a second, you may take comfort in knowing they're asking for a truly extravagant amount of time by fundamental standards. There is another reason to begin here, before definitions and theory, and the heavy machinery of modern physics. Planck time is often introduced as a number, and numbers this extreme can sometimes numb the mind rather than engage it. Say that something is unbelievably tiny, and the imagination nods politely, then wanders off. But if we begin instead with the idea that there may be a scale below which time as we understand it ceases to behave in any recognizable way, the concept becomes much more vivid. It stops being trivia and starts being a doorway. Not a doorway to easy answers, certainly, but to the frontier where cosmology, quantum theory and the nature of reality all begin stepping on one another's toes. And that frontier matters because the earliest universe seems to have passed through it. If we trace cosmic history backward, compressing everything toward the beginning, we eventually reach conditions so extreme that the known laws of physics stop giving a coherent account. The universe becomes hotter, denser, more energetic, and more curved until our usual descriptions fail. Somewhere in that near unimaginable early regime sits the Planck era, the domain where Planck time becomes relevant. It is not merely a microscopic curiosity, it is tied to the opening moments of everything we know. If we want to understand the universe at its deepest beginning, we eventually run into the Planck scale like travellers arriving at a border crossing with the wrong documents. So tonight we're starting at the threshold. Not with equations, not with technical machinery, and not with the kind of explanation that tries to sound impressive by moving too quickly. There is no need to rush a topic whose whole identity is based on being absurdly brief. We will take the slower route and let the strangeness reveal itself properly. We will ask what Planck time actually is, why physicists care about it, whether it truly represents a smallest unit of time or merely a limit of present knowledge, and what it tells us about the relationship between quantum theory and gravity. We will move from the familiar sense of time as a smooth experience toward the far stranger possibility that at the smallest scales time may not behave like a flow at all. That is the odd pleasure of subjects like this. The deeper you go into something tiny, the larger the questions become. A concept that begins as the shortest conceivable duration ends up forcing us to ask what time is, whether space and time are fundamental, how the universe began, and whether reality at its deepest level is continuous, discrete, emergent, or something we do not yet have words for. It is rather efficient in that way. A very small idea with a frankly unreasonable amount of philosophical luggage. For now, though, it is enough simply to sit with the central tension. Planck time is presented as the smallest meaningful interval of time in physics, yet no one can point to it on a clock. No process can be cleanly observed unfolding within it, and our theories do not fully agree on what lies beneath it. It is both a unit and a warning, both a scale and a mystery. It tells us that there is a point at which our neat descriptions of the universe no longer hold together, and that somewhere beyond that point a deeper theory is waiting to be found. And that is where we will continue, because before we can say whether Planck time is truly the smallest unit of time, we need to understand what it actually means to call any interval fundamental in the first place, and why physics chooses this particular scale instead of some other impressively tiny candidate. Once we step into that question, the idea begins to sharpen, and the smallest moment in the universe starts to look less like a simple fact and more like a crossroads where the deepest parts of modern physics meet. When physicists talk about Planck time, they are referring to an interval so extraordinarily small that it sits at the border of what our current theories can meaningfully describe. It is often introduced as the smallest meaningful unit of time, though that phrase deserves a bit of patience because it can suggest more certainty than physics is actually prepared to promise. Planck time is not simply a very, very short pause on a stopwatch. It is not a practical unit anyone uses for timing a process in a laboratory, baking a pie, or judging how long someone has been pretending to read the terms and conditions. It belongs to a very different category. It is a natural scale, built from the deepest ingredients in physics, and it marks a realm where our ordinary understanding of time begins to come apart. That is the first thing worth settling into. Planck time is not famous because it is tiny. Physics is full of tiny things. Electrons are tiny. Atomic nuclei are tiny. The wavelength of certain forms of light can be tiny. Tiny by itself is common enough. Planck time matters because it is the scale at which two very successful but very incompatible ways of describing reality appear to collide. One of those ways is general relativity, our best theory of gravity, space and time on cosmic scales. The other is quantum theory, our best account of the microscopic world. Each works brilliantly where it is meant to work, but when you try to push both into the same extreme conditions, especially at unimaginably small scales and immense energies, they stop cooperating gracefully. Planck time is the duration associated with that borderland. To make sense of that, it helps to step back and ask a more basic question. What do we usually mean by time? In everyday life, time is the medium in which change happens. You wake up, make tea, answer messages you had every intention of answering yesterday, look out the window, and by the time you notice, the afternoon has quietly appeared. Time seems smooth, continuous, and almost invisible. You do not usually experience it as a set of separate chunks arriving one after another like coins dropping into a slot. Instead, it feels like a seamless backdrop to everything else. Motion happens in time. Music unfolds in time. Thoughts drift in time. A clock does not create time. It simply helps you keep count of it. That smoothness is deeply intuitive. We speak of time as though it can be divided endlessly. Half a second, a quarter of a second, a thousandth, A millionth! We can keep shrinking the interval in language without hitting a built-in wall. Nothing in ordinary life tells us there must be a final smallest piece. If anything, our habits of thought encourage the opposite. We imagine that if something takes 1 second, it also takes 2/2 of a second, 4/4, and so on without limit. This way of thinking works perfectly well for daily life, and for a great deal of science. But once physics reaches its most extreme scales, the assumption that time can be subdivided forever begins to look less secure. Planck time enters here as a kind of warning light. It is the interval associated with the smallest scale at which our current theories can still speak with anything resembling confidence. Go below that scale, and the very concepts we use to describe the world, distance, duration, sequence, perhaps even cause and effect, may no longer behave in the familiar way. This is why physicists sometimes call it the smallest meaningful interval. Not necessarily because nature has stamped a sign saying no smaller units beyond this point, but because below this scale our present theories stop giving trustworthy answers. That difference is subtle, but it matters a great deal. If you hear smallest unit of time, it is natural to picture the universe as updating itself in discrete ticks, one Planck time after another, like a cosmic clock with incredibly ambitious specifications. But current physics does not actually prove that time is made of such little pieces. Some theoretical ideas suggest that it might be, others do not. What Planck time definitely tells us is that there is a scale where the known laws of physics run out of road. Whether that means time is fundamentally discrete, or whether it means we simply need a better theory is still open. Now, the reason this scale has such authority in physics is that it is not chosen arbitrarily. It is not the result of somebody deciding that this number looked especially dramatic in a textbook. It arises from combining a few of the most fundamental constants in nature, the basic quantities that appear to govern the structure of physical law itself. These are not conveniences like minutes or hours, which are shaped by human history and planetary motion. A minute is 60 seconds because of inherited cultural systems. An hour is 60 minutes because ancient counting habits have a very long afterlife. Planck time is different. It is meant to be natural in the strongest sense, built from ingredients the universe itself seems to use regardless of whether anyone is around to name them. That is one reason physicists take the Planck scale so seriously. It is not tied to Earth, to human biology, to calendars, or to the movement of the sun across the sky. If an alien civilization far away in another galaxy developed advanced physics, it would not care about our seconds, our months, or our Mondays. But it might still discover the same Planck scales because those are woven out of the same deep constants of nature. In that sense, Planck time belongs to a very special family of units. It tries to express something about the architecture of reality itself, rather than the preferences of clockmakers and civilizations. Even so, the concept can still feel slippery because Planck time is almost too small to imagine in a straightforward way. We are used to scales that can be compared with something sensory. A second is familiar. 1,000th of a second is very fast, but still tied to recognizable events, a blink, a camera shutter, the snap of a finger in the hands of an overconfident magician. But Planck time lives so far beyond sensory life that comparison breaks down. It is not just faster than a blink. It is smaller than the kind of intervals that even atomic processes routinely make look leisurely. It sits at a depth where language begins to lose its grip, and the mind starts nodding, while quietly admitting it cannot truly picture what is being discussed. And yet, physics does not ask us to picture it perfectly. It asks us to understand its role. Planck time tells us that there may be a shortest interval below which the distinction between before and after becomes physically uncertain, or at least inaccessible to our current theories. If you tried to probe time on even smaller scales, you would need to pack so much energy into such a tiny region that gravity itself would become impossible to ignore. Quantum uncertainty and gravitational effects would become entangled in a way neither of our major theories can currently handle on its own. The result is not a clear answer, but a collapse of the framework. Our usual tools for measuring and describing reality stop working neatly. This is where the idea becomes more than a numerical curiosity. It suggests that time, which feels smooth and obvious in ordinary experience, may not be fundamental in the way we instinctively think. Or perhaps it is fundamental, but not in a continuous way. Or perhaps the very question is slightly misguided, like asking what colour arithmetic is. Planck time sits at the point where such possibilities begin to feel less like philosophical games and more like serious physical questions. It also helps explain why the earliest moments of the universe remain so mysterious. When cosmologists speak about the beginning of the universe, they can describe a great deal with remarkable confidence, but only up to a point. As you trace the cosmos back toward its earlier state, temperatures rise, densities increase, and conditions become more extreme. Eventually you approach a regime where the universe is so compressed and energetic that the known laws of physics stop fitting together properly. That earliest region is often associated with the Planck era, a period before one Planck time had passed after the beginning. Beyond that boundary, or perhaps before it, depending on how cautiously one wants to speak, our current theories cannot provide a reliable description. It is not that physicists lack curiosity, they are full of it, often to a medically significant degree. It is that the mathematical tools we have were not built to survive those conditions intact. So in a very real sense, Planck time is also a horizon in knowledge. It marks the limit beyond which the universe becomes hidden behind the failure of our present theories. That makes it one of the most important scales in modern physics. It is not only about smallness, it is about where explanation stops and a deeper theory is required. Whenever a concept tells scientists both this is where everything becomes extreme and this is where your equations stop helping, it tends to attract attention. There is also something elegant about the way Planck time belongs to a broader family. There is a Planck length associated with an incredibly tiny distance and a Planck mass, surprisingly closer to ordinary scales than one might expect, at least by particle physics standards. Together, these Planck units define a natural system of scales where gravity, quantum theory, and relativity all become comparably important. This family resemblance matters because Planck time is not standing alone as some isolated oddity. It is part of a pattern. It is one expression of a deeper attempt to identify the point where our descriptions of nature must change character. And that brings us back to the phrase, what is Planck time? The safest answer is that it is the natural timescale at which the effects of quantum mechanics and gravity are expected to become equally significant, and where our current theories are no longer enough on their own. It is the interval light would take to cross the Planck length in the vacuum of space, though even that tidy verbal explanation risks sounding more concrete than the underlying physics truly is. It is not a measured tick of a cosmic clock. It is a derived scale, an indicator, a threshold. This threshold quality often gets lost in popular explanations. A great many simplified accounts say that nothing shorter than Planck time can exist, or that the universe literally updates once every Planck time. Such statements are easy to remember, but they slide from possibility into certainty too quickly. It is more accurate to say that intervals shorter than Planck time may not be physically meaningful within our current understanding, and that many physicists suspect some deeper structure of reality reveals itself there. Whether time itself is quantized, granular, emergent, or something stranger remains unsettled. That uncertainty should not be seen as a weakness. It is one of the healthiest features of serious science. A concept can be immensely important even if it points toward what we do not yet understand. In fact, some of the most fruitful ideas in physics are precisely those that tell us where our knowledge fails. The orbit of Mercury helped reveal limits in Newtonian gravity. Blackbody radiation exposed cracks in classical physics. The ultraviolet catastrophe, charmingly named for something that sounds like a failed holiday, helped usher in quantum theory. In the same spirit, Planck time tells us there is a place where the great frameworks of modern physics strain against one another hard enough that a new synthesis is needed. You can think of it as a kind of border crossing between established knowledge and speculative territory. On one side lie theories we can test and use with astonishing accuracy. On the other side lie proposals for quantum gravity, discrete space-time, strings, loops, emergent time, and other ambitious attempts to say what happens when the smooth geometry of relativity meets the probabilistic grain of the quantum world. Planck time stands at the gate, not necessarily as the final truth about time, but as the signpost everyone must pass. There is another subtle point hiding here, and it is worth slowing down for it. To ask whether Planck time is the smallest unit of time assumes that time is the kind of thing that comes in units. That may sound obvious, but it is not guaranteed. Temperature has units, but nobody imagines the world is built out of little temperature bricks. A meter is a unit of length, but the use of a unit does not by itself say whether space is continuous or discrete. In the same way, Planck time being a natural unit does not automatically prove that reality is composed of indivisible moments. It gives a scale, it highlights a limit, it may hint at discreteness, but it does not settle the matter by declaration. This is one reason the topic remains so rich. It forces us to separate the intuitive picture from the formal meaning. The intuitive picture says there must be a smallest tick. The formal meaning says only that our best current theories encounter a fundamental scale, where the known descriptions of time cease to behave reliably. The difference between those two statements is the difference between a solved puzzle and an active frontier. Even the phrase meaningful interval carries a little philosophical weight. Meaningful to whom? To a measuring device? To a physical process? To a theory? If you cannot, even in principle, build a device that distinguishes between two moments, separated by less than Planck time, without creating conditions so extreme that the concepts involved collapse, then perhaps the distinction itself has no physical meaning. That is one line of thought. Not because the interval is forbidden by logic, but because the universe may not allow such a distinction to be operationally defined. Physics often takes such operational limits seriously. If something cannot be measured even in principle, without undermining the framework of measurement itself, its status becomes delicate. This is where Planck time begins to feel less like a number, and more like a philosophical challenge issued by nature. It asks what it means to say that time exists at a scale where no known law can track it properly. It asks whether continuity is fundamental or approximate. It asks whether time is woven into the universe at the deepest level, or whether it emerges from something more primitive, the way temperature emerges from molecular motion, or a melody emerges from individual notes. These are not small questions, even if the interval that provokes them is vanishingly so. At the same time, there is something refreshing about how concrete the mystery is. This is not vague speculation for its own sake. Planck time arises from definite physical reasoning. It is anchored in the constants we trust most. It becomes relevant in the earliest universe near black holes, and in any serious attempt to unify quantum theory with gravity. It is mysterious, yes, but not in the manner of a foggy metaphor. It is mysterious in the manner of a locked door with very clear hinges. So if someone were to ask, in the calmest and most practical voice possible, what is Planck time, the best answer would be this. It is the natural timescale at which our current picture of the universe reaches one of its deepest limits. It is associated with the smallest interval that can be discussed meaningfully using the known constants of nature, before quantum effects and gravity become inseparable. It may be the smallest unit of time in a fundamental sense, or it may simply be the scale that reveals the incompleteness of our present theories. Either way, it is one of the clearest signs we have that time beneath its ordinary smooth appearance may be far stranger than it seems, and once that idea settles in, a new question starts to press forward naturally. If Planck time is not an arbitrary number, but a scale built from the deepest constants in physics, then why these constants? And why do they combine in such a way as to produce a boundary this remarkable? That is where the story becomes even more revealing, because the smallest meaningful interval of time does not appear from nowhere. It is assembled from the basic ingredients of the universe itself, and understanding those ingredients takes us much closer to why the Planck scale matters at all. To understand why Planck time is treated with such seriousness in physics, we need to look at what built it. Not the numerical value itself, and not yet the deep arguments about whether time is truly granular, but the ingredients from which this strange timescale is formed. Because Planck time is not something physicists invented in the casual way people invent units for convenience. It was not chosen because it sounds elegant, dramatic, or likely to impress undergraduates who have had too much coffee. It appears when you combine a small set of fundamental constants that seem to govern the structure of reality at the deepest level we currently know how to describe. In that sense, Planck time is not imposed on the universe, it is extracted from it. That idea is worth lingering over because it tells us something important about how physics thinks. There are many units we use every day that are shaped by human habits. A second, useful though it is, belongs partly to history. Its definition is now extremely precise, but the reason we have hours and minutes and seconds in the first place has a great deal to do with inherited systems of counting, and with the ancient human tendency to look at the sky and organise life accordingly. There is nothing wrong with that. It works beautifully. But such units are not written into nature in a universal sense. Another intelligent civilization could carve the day differently and still do perfectly good science. A Planck unit is different. It is meant to be natural in the strongest possible way. It is built not from cultural custom, but from the constants that keep appearing in our best descriptions of the world. If someone elsewhere in the universe discovered relativity, quantum theory, and gravity, they might not care in the slightest about our seconds, but they could still arrive at the same Planck scales. That is because the constants involved are not local conveniences, they seem to be part of the basic grammar of physical law. Now, the phrase fundamental constant can sound slightly grand, and physics is not always innocent when it comes to grand phrases. But here it really does mean something specific. A fundamental constant is a quantity that appears again and again in the laws of nature, always with the same value as far as we can tell, and sets the scale for how certain kinds of physical behaviour unfold. These constants are not decorative details, they are structural. Change them, and the universe as we know it would not behave the same way. Stars, atoms, radiation, motion, the very possibility of complex matter, all of it depends on the values of these constants. Planck time is built from three of the most important among them. One comes from relativity, one comes from quantum theory, and one comes from gravity. That is already a clue to why the resulting timescale matters so much. The moment you see those three great pillars of physics appearing together, you know you are approaching a boundary where the separate domains of our theories begin to overlap in an unusually deep way. The first of these constants is the speed of light in a vacuum. This is not simply the speed at which light happens to travel, though that description is common and not entirely wrong. In modern physics, it is something deeper than that. It is the fundamental conversion factor between space and time in relativity. The universal speed limit of causal influence, the rate at which massless signals propagate through the structure of space-time. It is woven into the geometry of the universe. Once Einstein reformulated our understanding of motion and simultaneity, the speed of light stopped being just an interesting property of radiation and became a central feature of reality itself. That matters because any timescale built using the speed of light carries with it the structure of space-time. It tells us that duration and distance cannot be treated as separate in the old intuitive way. A unit of time can be related to a unit of distance by asking how far light travels or how long light takes to cross some region. This is one reason Planck time is so closely related to Planck length. The two are not independent curiosities, they are linked through the speed of light. If Planck length is the tiny scale of distance where our theories begin to fail, then Planck time is the corresponding scale of duration, the time light would take to cross that distance in a vacuum. Already we can see the elegance of the construction. Time is not being treated in isolation. It is being tied to the geometry of space-time itself. But the speed of light alone does not get us to the Planck realm. For that, we need something from the quantum world. This brings us to the second constant, the one associated with quantum action. This constant sits at the heart of quantum theory. It tells us that the microscopic world is not infinitely smooth in the way classical physics once imagined. It sets the scale at which quantum effects become important, where energy, momentum, and related quantities stop behaving as though they can vary in the completely continuous classical manner without consequence. It is the reason the microscopic world does not simply mimic the macroscopic one at smaller sizes. If relativity gave us a universe in which space and time are woven together, quantum theory gave us a universe in which certainty itself is limited, measurement affects outcomes, and physical behavior comes in a form that resists purely classical intuition. When this quantum constant appears in the construction of Planck time, it signals that the smallest meaningful duration is not merely about geometry or motion. It is also about the quantum character of nature. At sufficiently small scales, you cannot ignore quantum uncertainty. You cannot assume that time and space remain the calm, clean stage on which events occur. The stage itself begins to shimmer conceptually. The quantum constant ensures that whatever Planck time is, it belongs not just to relativity, but also to the deep strangeness of the microscopic world. Then we come to the third constant, the gravitational constant. This one is perhaps less famous in everyday conversation, but it is indispensable. It tells us the strength of gravity, the degree to which mass and energy curve space-time and attract one another. In ordinary life, gravity seems familiar, almost dull in its reliability. Things fall, planets orbit. You place a biscuit too close to the edge of a table and physics demonstrates its priorities. But in fundamental theory, gravity is anything but dull. It is the one interaction that controls the large-scale structure of the universe. It shapes stars, galaxies, black holes, and cosmic expansion. And unlike the other forces, it has proven extraordinarily difficult to merge cleanly with quantum theory. That is why the gravitational constant is so important in the Planck construction. Without it, you can build scales relevant to quantum behavior or to relativity, but not to the point where gravity itself becomes quantum mechanically unavoidable. Once gravity enters the combination, the scale stops being merely small and starts being extreme in a more profound sense. It becomes the scale at which space-time itself is expected to feel the full strain of quantum uncertainty. Not matter moving around inside a smooth background, but the very geometry of reality becoming subject to quantum considerations. So when you place these three constants together, the speed of light, the quantum constant, and the gravitational constant, you are not just doing mathematical housekeeping. You're making a statement about where the three major conceptual pillars of modern physics all matter at once. That is what gives Planck time its special role. It is not just a small unit formed from arbitrary ingredients. It is the characteristic timescale of the domain, where relativity, quantum theory, and gravity all demand to be heard simultaneously. One way to appreciate this is to think about what happens when one of those ingredients is absent. If you ignore gravity, quantum theory and relativity can coexist reasonably well in the framework used for particle physics, and that framework has been enormously successful. If you ignore quantum effects, relativity and gravity give you a smooth classical space-time, good for planets, stars, and expanding universes. If you ignore relativity, quantum mechanics can still describe many microscopic systems to spectacular accuracy. The trouble begins when none of them can be neglected. When gravity is strong, scales are tiny, and quantum effects are unavoidable. That is exactly the territory marked by the Planck scale. This is why the constants that build Planck time matter even more than the number itself. The number is almost too extreme to picture, and if you focus only on how tiny it is, the idea can become oddly flat. But the construction tells a richer story. It says this timescale emerges from the deep architecture of physical law. It is what you get when you ask, in effect, for the natural unit of time that belongs to a universe governed by relativity, quantum mechanics, and gravity together. There is something almost satisfying about that, in the same way there is satisfaction in finding that three separate roads really do meet at one intersection. The constants are like roads laid down by different parts of physics, and Planck time is one of the places where they converge. That does not mean we fully understand what happens there. In fact, the opposite is true, but it means the location of the mystery is not random. Nature itself is pointing to it. Now, an important caution enters here. The fact that these constants can be combined to produce a timescale does not by itself prove that time literally comes in chunks of that size. Physics is more disciplined than that, at least on its better days. A natural scale can tell us where a theory changes character, where a new regime begins, or where our current models become insufficient, without automatically telling us that the world is discretized in the naive picture some people imagine. You can identify the scale at which a fluid stops behaving like a smooth continuum and starts revealing its molecular nature, but that does not mean every concept associated with the fluid was wrong. It means the description had a range of validity. In the same way, Planck time may mark the boundary beyond which the smooth continuum picture of time loses its reliability. That possibility becomes even more vivid when you remember that constants are not just numbers to plug into formulas. They tell us what kinds of things the universe cares about. The speed of light tells us that causality and space-time structure matter. The quantum constant tells us that uncertainty, discreteness in action, and the non-classical behaviour of microscopic systems matter. The gravitational constant tells us that energy and mass shape the geometry of the universe itself. When all three are brought together, the resulting scale is not arbitrary. It is the scale at which the universe stops allowing us to separate these concerns cleanly, and that is exactly why the Planck scale feels like such a deep threshold. At ordinary scales we can compartmentalise. We can study chemistry without worrying about black holes. We can calculate planetary orbits without worrying about quantum fluctuations in space-time. We can talk about clocks and seconds without asking whether time itself is emergent. But at the Planck scale, compartmentalisation fails. The constants themselves insist on a more unified story, one we do not yet fully possess. There is also a historical beauty in the fact that these constants came from very different scientific revolutions. The speed of light gained its deeper significance through relativity, a transformation in our understanding of motion and time. The quantum constant arose from the breakdown of classical physics in the microscopic world, especially in the study of radiation and energy. The gravitational constant emerged from the long effort to understand attraction, celestial motion, and the structure of the cosmos. Each constant carries the memory of a different scientific struggle. When they meet in the construction of Planck time, it is almost as though the major upheavals of modern physics are being compressed into a single scale. Max Planck himself understood the significance of natural units long before many later developments unfolded. He recognized that one could use fundamental constants to define units that were independent of human conventions. That idea was remarkably far-seeing. It suggested that beneath the local ways creatures measure the world, there might be a more universal system written into nature itself. In that vision, Planck units are not just convenient, they are revealing. They strip away the provincial features of human measurement and expose a set of scales that speak directly to the structure of physical law. This is part of what makes Planck time feel different from ordinary time units. A second tells you how we, or rather our inherited systems, choose to count time. Planck time tells you something about where space-time, quantum theory, and gravity all become equally unavoidable. One is a human measure refined to extraordinary precision. The other is a natural scale with philosophical consequences attached. Both are useful, but in very different ways. The more one sits with this, the stranger it becomes in a pleasingly scientific manner. Human life unfolds on scales that feel comfortable. We navigate by seconds, minutes, days, seasons, lifetimes. Biology, memory, and culture all live there. Even the finest technologies we use daily are still vast by comparison with the Planck scale. And yet hidden underneath all those familiar durations is this radically smaller threshold, built from the constants that seem to define the deep structure of the world. It is like discovering that beneath the smooth floorboards of ordinary experience lies a trapdoor leading into a region where our best maps no longer work. And because the constants that built Planck time come from the core theories of modern physics, they also tell us what kind of new theory is needed. Any successful deeper framework will have to explain why these constants combine the way they do, why this natural scale appears, and what really happens there. It will have to recover the familiar world at larger scales while making sense of the regime where the current theories overlap and fail. In that sense, Planck time is not just a boundary, it is a demand. It asks for a theory of quantum gravity, whether in the form of strings, loops, emergent space-time, causal sets, or something no one has yet imagined while pretending to be relaxed at a conference. It is tempting at this point to think of the constants as ingredients in a recipe, and that metaphor is not entirely useless. But it can make the process sound more mechanical than it really is. These are not just ingredients thrown together to see what happens. They're indicators of the deepest symmetries and limits we know. The speed of light tells you there is a fundamental structure to space-time and signal propagation. The quantum constant tells you the microscopic world does not permit classical exactness. The gravitational constant tells you geometry responds to energy and mass. Put them together, and the result is not merely a tiny tick. It is a crossroads where the most basic features of reality begin to interfere with one another in ways our current languages cannot fully capture. That is why the constants matter more than the scale they generate. Or perhaps it is better to say the scale matters because of the constants. The smallest tick is interesting precisely because it is built from the deepest things we know. It is not small by accident. It is small by necessity given the values and roles of the constants that govern our universe. And once that becomes clear, another question begins to rise naturally. If Planck time is constructed from these constants, and marks the scale where our descriptions start failing, then what exactly goes wrong if we try to divide time further? Why can we not simply keep slicing duration into ever smaller intervals the way ordinary intuition invites us to do? That is the next step in the story, because the idea of a smallest meaningful timescale only becomes fully interesting when we ask why endless division may stop making physical sense at all. One of the most natural assumptions we make about time is that it can always be divided further. A second can be split into halves, then quarters, then thousandths, then smaller again without any obvious reason to stop. The mind accepts this very easily because everyday life never gives us a reason to object. If a runner finishes a race in 10 seconds, we can measure more precisely. If a signal arrives in less than a second, we can still talk about milliseconds. If a chemical reaction happens faster than that, we move to microseconds, then nanoseconds, and onward into smaller and smaller intervals, as though time were an endless strip of fabric that can always be cut into finer threads. For nearly everything in ordinary experience, that habit works beautifully. Nothing around us seems to protest. Physics, however, has a long history of discovering that assumptions which feel harmless at ordinary scales become unstable when pushed far enough. Smoothness, continuity, separateness, even the difference between empty space and something happening within it, all of these ideas begin to misbehave when taken into extreme regimes. Time is no exception. The reason physicists take seriously the possibility that time cannot be divided forever is not because they are trying to be difficult, although the subject occasionally gives that impression. It is because our current theories strongly suggest that if we try to probe intervals smaller and smaller without limit, we eventually run into a wall built not from the engineering inconvenience, but from the combined structure of quantum theory and gravity. That is the important distinction. The issue is not simply that very tiny intervals are hard to measure. Hard problems do not usually stop physics for long. If something is merely difficult, physicists tend to build more sensitive instruments, invent better methods, and continue asking annoying questions until the universe reveals something useful. The trouble here is deeper. At sufficiently small scales, the very act of trying to define or measure a shorter interval forces so much disturbance into the system that the concepts involved begin to collapse. It is not that our clocks become clumsy. It is that the world itself may stop offering a stable notion of shorter and shorter intervals in the way classical intuition expects. To see why this happens, it helps to remember that measurement in physics is never pure thought floating above the world. To measure anything, you need a physical process. If you want to measure a distance, you need some interaction that marks positions. If you want to measure a time interval, you need something that changes in a regular way, some clock, some oscillation, some event that can be counted. Even the most refined clock is still a physical system. It is not exempt from the laws of nature. So when we talk about measuring extremely small intervals of time, we are really asking whether there can exist any physical process capable of distinguishing one moment from another at those scales. At ordinary scales, the answer is yes. We build better clocks. Pendulums gave way to quartz oscillators, and quartz gave way to atomic clocks of astonishing precision. Each improvement allowed us to resolve finer intervals. This history can create the impression that there is no fundamental obstacle, only a technological ladder waiting to be climbed. But as the scales get smaller, the ladder begins to lean against a different wall. To resolve shorter times, you typically need processes involving higher energies and shorter wavelengths. That is not an arbitrary inconvenience. It is built into the logic of how probing works. The smaller the interval you want to distinguish, the more concentrated and energetic your probe must be. Eventually you're no longer just observing time, you're battering spacetime with such intensity that it reacts. This is where quantum theory enters first. The quantum world does not permit unlimited exactness without consequence. The more precisely you try to pin down certain features of a system, the more uncertain other features become. That principle is often discussed in connection with position and momentum, but the broader lesson is what matters here. Nature does not hand out infinitely precise information for free. Precision requires conditions, and those conditions feed back into the system being measured. At sufficiently tiny intervals, a measurement is not a passive reading, it is a violent intervention. Now add gravity, and the problem becomes far more serious. Energy is not just something you spend in a measurement. In general relativity, energy affects the curvature of space-time itself. This is the crucial point. If you try to localize an event into an extremely tiny region, for an extremely tiny duration, you need to concentrate an enormous amount of energy there. But concentrated enough energy does not merely illuminate a region, it warps it. Push this logic far enough, and the act of trying to define the tiny interval begins to generate gravitational effects so strong that the region may no longer remain an open stage for measurement at all. It may, in the most extreme picture, collapse into something like a microscopic black hole, hiding the very details you are trying to resolve. That is one of the most famous intuitions behind the Planck scale. Below a certain threshold, trying to divide time further does not simply reveal finer detail, it destroys the meaningfulness of the question by dragging quantum uncertainty and gravitational collapse into the same tiny arena. The universe, in effect, seems to resist being sliced indefinitely with the conceptual knives we currently possess. This does not necessarily mean time is composed of little discrete blocks in the naive sense. That is a tempting picture, but it goes beyond what is firmly established. What it does mean is that the continuum picture of time, the idea that any interval can always be subdivided into a smaller, physically meaningful interval, without limit, may cease to be valid at the deepest scale. That is a profound shift. It tells us that the smoothness of time might be approximate, much like the smoothness of a tabletop. Run your fingers across wood, and it feels continuous enough. Look closer, and you find grain. Closer still, and you find molecules, then atoms, then fields and quantum structure. At each level, the earlier description was not exactly false. It was incomplete. Something similar may be true of time. It feels continuous because at human scales it is effectively so, but perhaps at the deepest level that continuity is no longer physically meaningful. There is also a conceptual issue hidden inside the phrase, divide time forever. To divide something forever assumes that it remains the same kind of thing at every scale. That assumption works for many mathematical objects. A line in geometry can be divided endlessly, because geometry, as an ideal structure, permits that. But physical reality is not obliged to behave like a mathematical abstraction in every respect. Physics often borrows the language of continuous mathematics because it is powerful and accurate across enormous domains, yet the success of a mathematical description does not guarantee that nature itself is constituted in the same manner all the way down. A fluid can be described continuously even though it is made of molecules. A metal rod can be treated as smooth in engineering even though atomic structure lies beneath. In the same spirit, time can be modelled as continuous over vast scales without requiring that infinite divisibility remain physically real at the smallest one. This is part of why the question matters so much. It is not merely about small numbers, it is about the relationship between mathematics and reality. Our equations often treat time as a continuous variable, and that treatment works astonishingly well in known regimes. But if the physical world does not support arbitrarily fine distinctions of duration, because any attempt to realize or measure such distinctions collapses the framework itself, then continuous time may be a remarkably successful approximation rather than the deepest truth. Another way to approach the issue is through causation. In ordinary thought, events line up in an order. One thing happens, then another. We imagine that between any two moments there must be room for still more moments. But at very tiny scales, even this ordering can become unstable. If space-time itself is subject to quantum fluctuations, then the clean background in which events are arranged may no longer remain fixed. The very notion of one event occurring at a sharply defined time before another may become blurred. It is difficult to keep dividing time if the structure that supports temporal order has itself become uncertain. This is where some theories of quantum gravity begin to take different paths. Some suggest that space-time is fundamentally discrete, built from minimal units or relationships rather than a smooth continuum. Others suggest that space-time, and perhaps time itself, is emergent, not fundamental at all, but arising from a deeper level of description that does not contain time in the ordinary sense. In both cases, endless divisibility becomes suspect. Either there is a smallest meaningful scale, or the whole question is misplaced because time is not basic enough to be cut like a loaf in the first place. The idea of emergence is especially interesting here because it allows for a strange kind of compromise. Time may appear continuous at large scales while failing to be fundamental underneath. Think of a film. When you watch it, motion appears smooth. The continuity is convincing enough that you stop thinking about individual frames, but that smoothness is produced, not basic. Or think of temperature. It feels like a simple property, but it emerges from the collective behavior of many particles. Individual molecules do not possess temperature in the same way a cup of tea does. In a similar manner, time might be something that appears smooth and flowing only at scales where vast numbers of underlying interactions average into a stable description. Divide too far, and the notion of time as a continuous flow may stop being the right language. Even if one does not commit to any particular theory, the pressure against infinite divisibility remains strong. The union of quantum principles and gravitational reasoning tells us that to investigate ever smaller intervals, we require ever more extreme conditions, and those conditions eventually undermine the very assumptions that made the investigation meaningful. That is not a technical annoyance. It is a conceptual limit. It tells us that the universe may not support the fantasy of infinite resolution. There is something almost philosophical about this, though it comes directly from physics. Human thought is very fond of the infinite. We like to imagine unending sequences, endless divisibility, boundless extension. Mathematics handles such ideas with grace. Nature perhaps does not always join in. The physical world may be finite in the ways that matter for observation and structure, even when our symbols invite us onward. In that sense, Planck scale reasoning is a reminder that not every mathematically imaginable distinction must correspond to something physically real. One can also see why this conclusion is difficult to accept emotionally, even if intellectually it makes sense. Infinite divisibility feels like freedom. It suggests that there is always more detail to uncover, always another layer beneath the layer. To discover that this may not hold for time can feel like arriving at the bottom of a staircase you assumed would continue forever. But physics has delivered such corrections before. Matter once seemed infinitely divisible until atoms, then subatomic structure, then quantum fields changed the picture. Space once seemed a passive container until relativity turned it into a dynamic participant. Time itself once seemed universal until relativity showed it depends on motion and gravity. The possibility that time cannot be divided forever fits this tradition rather well. Another comforting intuition gently escorted toward the exit. There is also an important operational angle. In physics, meaningful distinctions are often tied to what can in principle be measured or interacted with, not merely what can be imagined abstractly. If no physical process can distinguish between two intervals shorter than a certain scale, because any attempt would collapse into uncertainty or gravitational obstruction, then those distinctions may not belong to physical reality in a robust sense. This does not prove that sub-plankian durations are logically impossible. Physics is not in the business of policing logic with a clipboard, but it does suggest that such durations may be physically empty within our current understanding. The world may not contain the machinery required to make them matter. That phrase physically empty is useful because it helps avoid overstatement. The claim is not necessarily that smaller intervals cannot exist in any imaginable, metaphysical sense. The claim is that our best theory suggests such intervals may not be physically meaningful, measurable, or describable. That is a subtler and more responsible statement, and science tends to fare better when it resists the urge to sound more certain than the evidence warrants. Still, one should not underestimate how radical even that modest statement is. If time cannot be divided forever in a physically meaningful way, then the smooth continuum of temporal passage is not a bottom-level fact. It is either limited, emergent, or both. That would affect not just technical physics, but our broader metaphysical picture of reality. Continuity, sequence, motion, and change would all need to be understood in light of a scale beneath which the ordinary language of before and after may stop applying cleanly. Consider motion for a moment. We usually think of motion as something that happens continuously through time. An object moves from one place to another by occupying intermediate positions at intermediate times. But if time loses its ordinary divisibility at the deeper scale, then motion cannot simply be what it seems in classical intuition. That does not mean motion becomes unreal. It means the classical picture may be an approximation emerging from a deeper structure. Much as a digital image can still show smooth curves when viewed at the proper distance, the world can exhibit smooth motion even if the underlying description is not continuously divisible in the way we naively imagine. This line of thought also sheds light on why the earliest universe remains so elusive. As we trace cosmic history back toward the beginning, we are tempted to ask what happened at earlier and earlier moments. But if time itself ceases to be meaningfully divisible below the Planck scale, then the demand for an earlier and still earlier physical account may begin to fail. The question may not have the straightforward form we assume. It is possible that before a certain threshold, the structure of time is no longer available in the sense required by the question. That possibility is one reason cosmology becomes so conceptually delicate near the origin. the failure is not just one of data, it may be one of language. There is a quiet irony in all this. The urge to divide time forever comes from a very natural human confidence in analysis. If something is unclear, break it down. If a process seems long, measure smaller pieces. If a concept is vague, refine it. This method has served science brilliantly, but here it may encounter a domain where refinement stops revealing a deeper layer of the same kind, and instead reveals a transition into a different kind of reality altogether. There may be no endlessly finer version of ordinary time waiting below. There may be a threshold at which the concept itself changes character. Some physicists are quite comfortable with this possibility. Others remain cautious, preferring to say that our theories currently fail there, and leaving open the hope that a future framework will restore continuity in some unexpected way. That caution is wise. The history of physics includes many cases where apparent limits turned out to be signs of incomplete theory rather than final features of nature. Yet even that cautious attitude still acknowledges the present fact that infinite divisibility has no secure support at the Planck scale. Whatever lies there, it is not simply more of the same, and this is why the phrase smallest meaningful interval remains so powerful. Meaningful is doing a great deal of work. It carries the idea that physics is not only about what can be written on paper, but about what can be distinguished, measured, defined, and woven into coherent law. If the distinction between one moment and another below a certain scale cannot be made without destroying the framework that gives the distinction sense, then the endless ladder of subdivision may end not with a final brick, but with the disappearance of the staircase. That image may sound dramatic, but the science underneath it is sober. Quantum theory resists infinite precision. Gravity makes energy physically consequential for space-time itself. Attempts to probe smaller intervals require greater concentration of energy. Greater concentration of energy bends geometry more strongly. Push the combination far enough, and the ordinary meaning of measurement disintegrates. From that reasoning comes the suspicion, and in many approaches the expectation, that time cannot be divided forever in the physically meaningful way classical intuition assumes. Once you sit with that for a while, the smooth seconds of daily life begin to feel slightly more mysterious. Not false, not illusory, but layered. The time we inhabit may be like the calm surface of a deep sea whose bottom cannot be reached by simply swimming downward forever with the same stroke. At some depth, the water itself changes character. The pressure builds. The known rules stop being enough. And although we are still far above that depth in everyday existence, the existence of such a threshold tells us something profound about the universe. Time is not merely there to be sliced without end. It may have a structure, a limit, or a hidden origin more subtle than continuity alone suggests. And that brings us naturally to the next stage of the story. If there is a scale beneath which further division of time loses physical meaning, then the earliest universe becomes an especially strange place to examine, because there was a period when the cosmos itself was compressed into conditions near that threshold. To understand Planck time more fully, we have to ask what the universe was like when it was younger than such a moment, and why that beginning remains one of the most difficult frontiers in all of physics. To imagine a universe younger than a Planck moment is to arrive at one of the strangest edges in all of physics, because this is the point where even our best scientific language begins to hesitate. Usually when we tell the story of the universe, we do so with a kind of chronological confidence. We move backward through time from galaxies to early stars, from stars to glowing plasma, from plasma to an even hotter and denser state, and we keep going as though history is simply a film we can rewind. At first, that method works astonishingly well. Modern cosmology has traced the broad outline of cosmic history with impressive success. We can describe the expansion of the universe, the cooling of matter and radiation, the emergence of nuclei, atoms, stars, galaxies, and all the long unfolding structure that eventually leads, through a slightly unreasonable chain of events, to sleepy humans listening to discussions of the smallest unit of time. But there comes a point very near the beginning where this backward journey stops being a matter of simply rewinding further. The universe becomes so hot, so dense, and so compressed that the ordinary tools of cosmology begin to fail. General relativity, our theory of gravity and space-time, can be pushed back extremely far. Quantum theory, our theory of the microscopic world, can also describe extreme conditions of energy and matter. Yet when the universe is younger than a Planck moment, those two theories can no longer be kept politely in separate rooms. They demand to be used at the same time, under the most extreme conditions imaginable, and we do not yet possess a completed theory capable of doing that. So when people ask what the universe was like before one Planck time had passed, the honest answer is not a neat picture, but a boundary. It is a place where knowledge becomes thin. That is what makes this era so fascinating. A universe younger than a Planck moment is not just very young in the casual sense. It is young enough that the distinction between time as we usually understand it and whatever deeper structure underlies reality may not yet have settled into recognizable form. It is not merely that the universe was smaller or hotter. Those are familiar ideas. It is that the framework in which we normally place such descriptions, the smooth stage of space-time itself, may no longer have existed in any ordinary sense. When we say younger than a Planck moment, we are speaking of a regime where our concepts of before and after, distance and duration, may not have been physically meaningful in the way they become later. This is worth pausing over because it runs against one of our strongest habits of thought. We are used to imagining beginnings as the earliest point in an already familiar framework. If you ask about the beginning of a conversation, you picture the first words. If you ask about the beginning of a journey, you picture the moment of departure. Even the beginning of a life is imagined as the first stage in a developing sequence. In each case, time is already there, acting as the container in which the beginning occurs, but the very early universe may not fit that pattern. The beginning may not be an event inside time so much as the point where time, at least in the usable physical sense, becomes definable at all. That is a much stranger possibility, and one Planck moment takes us right up to its doorstep. When cosmologists speak carefully, they usually avoid pretending that we know what happened at sub-plankian times. They can model the universe from very early moments onward with increasing confidence once the conditions become less extreme. But before that threshold, the equations we rely on begin to lose their authority. If we trace the expansion of the universe backward using general relativity alone, space-time curvature and density grow without bound, and we run into what is called a singularity, a point where the theory itself breaks down. Singularities are often less a feature of nature than a confession from a theory that it has been pushed beyond its proper range. In this case, the confession is a loud one. It tells us that classical space-time cannot be the whole story. Quantum effects must enter, and once they do, the very geometry of the universe is no longer something we can treat as smooth and fixed. So what might the universe have been like younger than a Planck moment? The cautious answer is that we do not know. But that uncertainty is not empty. It is structured uncertainty, shaped by the reasons our current theories fail there. We know that energy densities would have been enormous beyond anything later in cosmic history. We know that quantum fluctuations could not have been ignored. We know that gravity would have been too strong to remain classical. We know that our ordinary picture of space as a continuous arena and time as a smooth flow would have been under extreme pressure. These clues do not give us a finished portrait, but they do tell us what sort of portrait any future theory must be able to paint. One possibility is that space-time itself was undergoing quantum fluctuations so violent that the familiar notion of a stable geometric background simply did not exist. At human scales, and even at stellar or galactic scales, space-time behaves smoothly enough that we can treat it as a reliable structure. Objects move through it. Light travels through it. Gravity curves it. But at the Planck scale, some physicists suspect that space-time becomes more like a restless quantum medium, no longer smooth but fluctuating in a way that resists ordinary description. The phrase quantum foam is sometimes used for this idea, though it should be taken as a suggestive metaphor rather than a tidy visual model. It captures the thought that at unimaginably small scales, space-time may be turbulent, uncertain, and incapable of supporting the clean notions of duration and distance that larger scales take for granted. If that is even partly right, then asking what happened before one Planck moment may be like asking for the precise shape of a wave before the ocean exists in any calm, recognizable form. The question still points towards something real, but its familiar wording begins to mislead us. We want a sequence of earlier and later events, yet the very medium that allows such a sequence may not have stabilized. In that sense, a universe younger than a Planck moment may not be something we can narrate in ordinary temporal language without quietly smuggling in assumptions that no longer hold. There is also the possibility that time itself is emergent. This idea appears in several approaches to quantum gravity and in various philosophical reflections on modern physics. On this view, time is not a basic ingredient of reality all the way down. Instead, it arises from deeper relationships, perhaps from entanglement, perhaps from causal structure, perhaps from something even more abstract that does not resemble time in the usual sense. If that turns out to be true, then the earliest universe may have existed in a condition where time had not yet emerged as the kind of dimension we experience. To say younger than a Planck moment would then be slightly awkward language, because it would use temporal ordering to describe a regime that might not yet possess time in the familiar form. This sounds dramatic, but it is not mere wordplay. Physics has already taught us that intuitive categories often emerge rather than stand at the foundation. Temperature emerges from microscopic motion. Solidity emerges from electromagnetic interactions and quantum structure, rather than being a primitive feature of matter. Even the smoothness of many materials emerges only when viewed at scales large compared with their microscopic grain. Time may be another such case. It may feel foundational, because every human experience unfolds within it, yet that does not guarantee it is fundamental in the deepest description of the universe. A universe younger than a Planck moment is also interesting, because it sharpens the question of origin. People often ask what happened before the Big Bang, as though the universe must have had a prior chapter waiting just outside the first page. Perhaps it did. Some theories suggest cosmic bounces, cyclical histories, or pre-existing states from which our observable universe emerged. Others suggest inflationary scenarios tied to deeper multiverse structures. Still others imply that the very notion of before the Big Bang may be misguided because time itself begins with the universe in the relevant sense. The Planck era sits right at the centre of these possibilities. We cannot answer the question of cosmic origin properly without understanding what happens when the universe is compressed to Planckian conditions, and at present that understanding remains incomplete. That incompleteness is not a failure of curiosity. It is the natural consequence of trying to ask the universe about its most extreme state, using theories that were developed in regimes where space-time is already well behaved. General relativity is magnificent, but it treats space-time classically. Quantum theory is magnificent, but it usually assumes a background time parameter rather than explaining time itself. When we ask about a universe younger than a Planck moment, we are asking for a description of reality in a regime where the background, the geometry, the causal order, and the quantum behavior all become inseparable. It is rather like asking two translators, each excellent in one language, to jointly interpret a sentence written in a third language that neither fully knows. They will do their best. They may catch fragments, but the full meaning will escape them until someone learns the deeper grammar. There is something humbling about the fact that the earliest conceivable moment in cosmic history is not simply hidden by distance or dimness, but by theory. Most mysteries in astronomy involve looking farther, waiting longer, detecting weaker signals, or building more sensitive instruments. This one is different. Even if one had perfect observational access to the earliest universe, one would still need the right conceptual framework to understand what was being seen. The barrier is not only practical, It is foundational. Until quantum gravity is understood in a robust way, the universe younger than a Planck moment remains a region glimpsed mostly by the shadows it casts on our incomplete theories. Yet those shadows are not useless. In fact, they have guided enormous efforts in theoretical physics. String theory, loop quantum gravity, causal set approaches, asymptotic safety programs, and other attempts at a deeper framework all in their own ways confront the question of what happens at Planckian scales. Some suggest space-time is not continuous but built from more primitive discrete structures. Some suggest geometry emerges from entanglement or deeper symmetries. Some suggest the singularity is replaced by a bounce, avoiding the classical breakdown entirely. Others propose that the very language of space-time must be reformulated from the ground up. These approaches differ in methods and ambitions, but they all agree on one point. A universe younger than a Planck moment cannot be described adequately by simply extending familiar ideas without change. It is also worth noting that even though we cannot describe this era directly with confidence, it may still leave traces. The universe we observe today bears the imprint of its early conditions, subtle features in cosmic structure, patterns in background radiation, or the behavior of gravity and quantum fields at high energies may eventually reveal clues about what sort of deeper theory governs the Planck regime. In that sense, the earliest universe is not entirely sealed off. It is hidden, yes, but not necessarily mute. It may still whisper through the large-scale structure of the cosmos, through black hole physics, through the nature of vacuum energy, or through some currently unrecognized phenomenon waiting patiently for a sufficiently curious species to notice. There is a pleasing irony here. The youngest universe is, in one sense, the most ancient thing we can ask about. It lies at the beginning of all known history, yet it also belongs to the farthest frontier of present knowledge. The closer we move toward the start, the more speculative the terrain becomes, until eventually we're dealing not with settled description, but with the possibility that description itself must be reinvented. That makes the Planck era one of those rare scientific topics that is both highly technical and deeply philosophical. It forces us to ask not only what the universe was like, but what it means for anything to be like something, at a stage where time and geometry may not yet exist in recognizable form. This is also why one must resist the urge to make the story too neat. Popular explanations often present the early universe as a sequence of increasingly familiar snapshots, just hotter and denser. That narrative is useful for much of cosmic history, but it breaks down near the beginning. A universe younger than a Planck moment is not simply a smaller version of the later universe. It is a different conceptual regime. The difference is not one of degree alone. It may be one of kind. Before that threshold, we may not be dealing with matter and space-time in the forms we later recognize, but with a more primitive layer of reality from which those categories emerge. Even the word younger becomes slippery here. Age assumes a meaningful time parameter. If time itself is unsettled or emergent at these scales, then saying the universe is younger than a Planck moment may be more like using the best available approximation than stating a fully literal fact. It is how we gesture toward the earliest accessible boundary of our current theories. The phrase is still useful, but it comes with an asterisk large enough to make a cosmologist sigh gently into their tea. Still, there is real value in staying close to the threshold, rather than pretending to leap across it. Science advances not only by answering questions, but by clarifying which questions are well formed, and which are not yet ready to be asked in their familiar shape. The Planck era teaches exactly that lesson. It says that the earliest universe is not simply waiting for us to rewind further with the same conceptual machinery. It may require new categories altogether. That realization is not a dead end. It is a map of where discovery must go next, and perhaps that is the most interesting feature of a universe younger than a Planck moment. It marks the place where cosmology becomes inseparable from the fundamental nature of time itself. You cannot ask what the universe was doing then without also asking what time means, what space means, what causation means, and whether the smooth backdrop of existence is truly basic or only an emergent convenience of larger scales. In that sense, the youngest universe is also the most revealing. It exposes the assumptions hidden inside our everyday picture of reality by pushing them until they bend. The more one thinks about it, the more the Planck moment begins to look less like a tiny unit on a cosmic clock and more like a conceptual border crossing. On one side lies the universe we can describe with increasing confidence, even when it is astonishingly young, hot, and dense. On the other side lies a regime where our theories stop agreeing on what the words space and time should even mean. That is why the Planck era remains both frustrating and irresistible. It is where knowledge becomes uncertain for the best possible reason, because the universe is inviting us to find a deeper language. And that invitation leads naturally onward, because if a universe younger than a Planck moment resists description, due to the breakdown of ordinary space-time, then the next thing we need to examine is the idea that space-time itself may have been born, or at least stabilized around that threshold. In other words, if the Planck era hides the origin of meaningful temporal and spatial structure, then we are brought to the question of how space-time as we know it may have emerged at all. When we talk about Planck time and the birth of space-time, we're moving into a part of physics where the usual order of explanation begins to wobble a little. In most subjects, time is treated as something already available. It is the background in which things unfold. Space is there too, the stage on which matter moves and light travels. We're used to treating both as givens, even when relativity taught us that space and time are woven together into a single structure. The resulting picture was still in many ways manageable. Space-time could bend, stretch, and respond to matter and energy, but it was still the thing within which physical events occurred. It remained the arena. The Planck scale changes that comfort. It suggests that if we go back far enough or push deep enough into the smaller scales, space-time itself may stop being a stable arena and become instead something unfinished, unstable, or perhaps not yet fully meaningful in the way we later understand it. That is why the phrase birth of space-time is not just decorative language. It reflects a serious possibility in modern physics. There may have been a regime in the earliest universe where the familiar structure of space and time had not yet emerged in a recognizable form. Planck time marks the threshold where this possibility becomes unavoidable. It is the interval associated with the scale at which gravity and quantum effects become inseparable, and once that happens, the smooth geometric picture of space-time given by general relativity can no longer be trusted on its own. If classical space-time fails there, then one natural question follows. Did space-time have to emerge from something deeper? And if so, is the Planck era the period when that emergence took place? This is one of the most radical shifts in modern theoretical thinking. For a long time, even sophisticated physics still assumed that space and time were basic ingredients of reality, though their properties might be more subtle than common sense suggests. Quantum theory complicated matter and measurement. Relativity complicated motion and simultaneity. But the idea that space-time itself might not be fundamental, that it could arise from a deeper layer of reality, is a newer and more unsettling development. It asks us to imagine that what seems like the most obvious backdrop of existence may be more like a large-scale appearance, something real and reliable at our scale, but not ultimate. There are good reasons this idea has gained traction. The first is simply that our current theories divide responsibility in an awkward way. General relativity gives us a magnificent description of gravity as the curvature of space-time. In that theory, space-time is not passive. It bends in response to energy and mass, but it is still treated classically as a smooth geometric structure. Quantum theory, on the other hand, describes matter and fields in ways that are probabilistic, uncertain, and deeply non-classical. Yet standard quantum theory often assumes a fixed background time parameter rather than explaining time itself. Each theory is powerful, but they are built on different assumptions about the status of space-time. At the Planck scale, those assumptions crash into one another. That collision is one reason many physicists suspect that space-time, as presently understood, cannot be the bottom layer of the story. To think clearly about this, it helps to distinguish between space-time as experienced and space-time as fundamental. As experienced, space-time is extraordinarily robust. We move through space, we age through time, distances can be measured, durations can be compared. Gravity affects clocks and trajectories, but the structure remains coherent enough that life, engineering and astronomy can function. Even relativity, for all its strangeness, still offers a stable space-time picture, just one that is dynamic and observer-dependent in certain respects. At large scales, this works beautifully. But fundamental does not mean useful at large scales. It means irreducible. It means not emerging from anything more basic. And Planck's scale reasoning gives us increasing cause to doubt that space-time is fundamental in that strongest sense. One way to see why is to remember what goes wrong near the Planck scale. If you try to probe smaller and smaller distances or shorter and shorter times, quantum uncertainty forces you to use increasingly energetic probes. But energy curves space-time, so the very act of trying to resolve fine structure begins to disturb the geometry you're trying to study. Eventually, the disturbance becomes so severe that the smooth geometry of space-time is no longer a reliable concept. At that point, asking for the exact shape of space-time becomes a little like asking for the exact position of a wave on a sea that is exploding into spray. The background has ceased to be background. This suggests that the smooth space-time of general relativity may be comparable to a large-scale approximation, much as the smoothness of a fluid is an approximation that works only above the molecular scale. Water in a glass can be treated as continuous for many purposes. You can talk about waves, currents and pressure without mentioning molecules. But if you push the description far enough down, the continuum picture breaks and molecular structure takes over. Some physicists suspect space-time behaves similarly. At everyday and astronomical scales, it is effectively smooth, but at the Planck scale, some deeper structure may replace the continuum. If that is correct, then the Planck era may represent the transition from whatever that deeper structure is into the stable space-time we later recognize. In other words, the birth of space-time may not refer to a dramatic moment when empty space suddenly popped into being like a stage set rising from the floor. It may instead refer to the emergence of a coherent geometric order from a more primitive regime where the notions of distance, duration and causal order were not yet settled in the familiar way. That is a subtler picture, but probably a more realistic one. Several approaches to quantum gravity explore this possibility from different angles. Some propose that space-time is built from discrete elements. Others suggest it arises from networks of relations. Still others treat geometry as something encoded in patterns of quantum entanglement. These approaches differ greatly in detail, but they share a common instinct. The familiar continuum of space and time may be emergent, not fundamental. Planck time then becomes significant because it marks the scale where the emergent description becomes unreliable and the deeper layer must take over. Take the idea of discrete space-time, for example. In some approaches, space-time is not infinitely divisible. Instead, there may be a minimal scale of area, volume, or interval, and what we call geometry emerges from the arrangement of these underlying units or relationships. This does not necessarily mean reality looks like a neat lattice or a cosmic graph paper, which would be too tidy and perhaps too flattering to the human love of grids. The discrete structure, if it exists, could be far subtler than that. But the key point is that smooth continuity would no longer be the foundation. It would be a large-scale appearance, like the apparent smoothness of a digital image viewed from far enough away. Other approaches place less emphasis on discreteness and more on relational structure. In these views, what matters fundamentally may not be positions in pre-existing space or moments in pre-existing time, but the relations among events or quantum states. Space and time then emerge as effective ways of organizing those relations once the system becomes large and stable enough. This is an appealing idea because it fits a broader pattern in physics. Again and again, properties that seem basic at one level turn out to emerge from patterns at a deeper one. Pressure emerges from molecular collisions. Temperature emerges from collective motion. Solidity emerges from field interactions and quantum exclusion. Perhaps spacetime too is what a deeper level looks like when viewed from the scale where continuity becomes useful. The Planck time threshold is important in all of these pictures because it marks the region where the old language becomes inadequate. Before or below that scale, it may not make sense to ask exactly how far apart two events are, or how long a process takes, because the framework in which those questions are posed has not yet stabilized. That is a striking thought. We're so used to time and space being available that it feels almost impossible to picture their absence or incompleteness. But perhaps picturing it is the wrong goal. Physics may eventually describe such a regime mathematically and conceptually without giving us an image that feels intuitive. That would hardly be unprecedented. Modern physics has done that many times already. The birth of spacetime also raises a delicate issue about beginnings. When people hear that spacetime may have emerged, they often imagine a before in which something else existed. But the word before is already temporal. If time itself is what is emerging, then saying what came before it may be like asking what lies north of the North Pole. The question may use a meaningful word in a context where it loses its footing. That does not prove there was no deeper precursor state. There may well have been. Some theories suggest prior phases, bounces, or pre-geometric structures. But it does mean that ordinary temporal language becomes risky here. We cannot casually assume that there was a conventional sequence of moments waiting in a temporal corridor behind the first emergence of time. This is one reason cosmology near the Planck era becomes both exciting and frustrating. We want a narrative. Human beings adore narrative. We want the universe to begin in one state, pass into another, then another, until eventually stars form and someone invents the kettle. But if time itself is part of what is being born, the narrative structure may have to be reconstructed from something more primitive. The beginning may not be a first scene in a familiar timeline. It may be the point at which a timeline becomes a meaningful concept at all. That possibility has philosophical consequences, but it also has physical ones. If space-time is emergent, then gravity may be emergent as well, at least in the geometric sense described by general relativity. That would mean the curvature of space-time is not the ultimate language of gravity, but a large-scale expression of deeper degrees of freedom. Some ideas in theoretical physics take exactly this route. They try to derive space-time geometry from quantum information, thermodynamic principles, or other more basic structures. In such pictures, the birth of space-time is closely tied to the emergence of the laws we currently use to describe gravity and cosmic evolution. This is deeply interesting because it changes what we mean by explanation. In classical cosmology, one asks how the universe evolved within space-time. In a more fundamental picture, one may need to ask how space-time itself emerged from a deeper substrate. That is a much more ambitious question. It shifts the target of explanation from events in the universe to the conditions that make a universe with events possible in the first place. Planck time is central to this shift because it provides the natural scale at which the transition likely matters. At times, much later than the Planck era, spacetime appears smooth enough that general relativity becomes an excellent description. At scales much larger than the Planck length, geometry behaves continuously enough that we can ignore whatever fine structure may lie beneath. But near the Planck threshold, the emergent story becomes unavoidable. This is the zone where the old effective description breaks and the deeper one must begin. There is also a reason the Planck scale, rather than some arbitrary tiny scale, is associated with this birth. It comes from the meeting of the constants that govern relativity, quantum mechanics, and gravity. That convergence is not a coincidence. It tells us that the Planck regime is the point where all three domains matter equally. And since spacetime sits at the heart of relativity, while quantum mechanics questions the smoothness and determinacy of the microscopic world, their intersection naturally targets the status of spacetime itself. The Planck scale is where the old picture becomes impossible to preserve without change. Some theories imagine that what emerges from the Planck regime is not just space-time, but causal structure as well. Causality, the ordering of events into before and after, cause and effect, may itself be part of the large-scale organisation that only becomes stable after the Planck era. If so, then the birth of space-time includes the birth of meaningful sequence. That is a powerful idea. It suggests that the temporal order we rely on, the very scaffold of explanation, may not be primitive. It may be one of the things that condense out of a deeper level of reality. This helps explain why questions about the earliest universe can become so slippery. We keep asking what happened first, what came before, what caused what. But those are causal and temporal questions, and the Planck regime may be precisely where causal and temporal structure become unclear. We may need a description that does not begin with chronology, but gives rise to chronology as an emergent pattern. That sounds almost perverse to ordinary reasoning. Yet modern physics has repeatedly forced us to accept that the deepest level may not resemble the categories through which we first encounter the world. Another useful comparison comes from condensed matter physics, where large-scale properties emerge from collective behaviour that individual components do not visibly possess. A crystal has rigidity, but a single atom does not have rigidity in that same sense. A fluid has viscosity, but no lone molecule is viscous. These properties appear at the collective level. If space-time behaves similarly, then its smooth geometry and temporal ordering may be collective features of an underlying quantum system. The Planck era would then be the region where the collective order had not yet fully formed, or where it fluctuated so strongly that stable space-time had not settled in. That idea has a certain elegance. It turns the birth of space-time into something more physical and less theatrical. Rather than a mysterious appearance from nothing, one has an emergence of order from more primitive structure. The trouble, of course, is that we do not yet know with confidence what that primitive structure is. Different theories offer different candidates, and none has yet achieved decisive empirical confirmation. So while the broad idea of emergent space-time is powerful and increasingly influential, the details remain open. The birth of space-time is a live frontier, not a finished chapter in a textbook. Still, one can see why the idea keeps returning. It solves, or at least reframes, several deep tensions at once. It explains why classical space-time fails at the Planck scale, without requiring us to abandon its success at larger scales. It makes sense of why time and space might lose ordinary meaning in the earliest universe. It opens a path toward unifying gravity with quantum theory. And it transforms Planck time from a mere tiny interval into a threshold of ontological change, the boundary between an underlying regime and the emergence of the arena in which familiar physics unfolds. There is also something quietly profound in the thought that space-time might have a birth, because so much of human experience depends on it. Every memory, every movement, every act of waiting, every sunrise and conversation, and long, awkward silence exists within the framework of space and time. To learn that this framework may itself be contingent, emergent, and perhaps historically formed in the earliest universe is to realize that even the stage of existence may have a history. Not just the actors, not just the script, but the stage itself. At the same time, one should be careful not to let the language run too far ahead of the evidence. We do not yet know exactly how space-time emerges, or whether emergence is the right final picture. It may turn out that space-time is fundamental after all, but behaves quantum mechanically in a way we have not yet fully understood. Or it may be partly emergent, with some features basic and others effective. Physics is not finished here, and anyone who sounds entirely certain about the deepest origin of space-time is probably enjoying the feeling of certainty more than the discipline of science. What we can say with confidence is more limited but still remarkable. Planck time marks the scale where classical space-time can no longer be assumed reliable. The earliest universe likely passed through a regime where quantum gravity effects were essential. Any successful theory of that regime will have to explain how the stable spacetime of later cosmology arises. That is already enough to justify talking about Planck time and the birth of spacetime in the same breath. The smallest meaningful interval is not merely a curiosity. It may be tied to the very moment when the universe first became a place where duration and distance made coherent sense. And once one accepts that possibility, the next challenge comes into focus. If the Planck scale is where spacetime emerges and where our two great theories fail to merge smoothly, then the central problem is no longer just the early universe. It is the deeper conflict between quantum physics and gravity. That conflict is the engine behind almost every mystery we have been circling, and understanding it is the next necessary step if we want to know why the smallest tick in the universe carries so much significance. The reason Planck time matters so much, and the reason the earliest universe becomes so difficult to describe, is that it sits exactly where quantum physics meets gravity. That meeting is not a polite academic exchange. It is more like two brilliant thinkers arriving with incompatible assumptions about how reality is organized, and then discovering they both need to explain the same event. Each theory is enormously successful in its own domain. Quantum physics gives us the microscopic world with all its uncertainty, probability and strange non-classical behavior. Gravity, in the form of general relativity, gives us the large-scale structure of space-time, the motion of planets, the bending of light, black holes, and cosmic expansion. If you stay within the regime where one theory dominates, everything works beautifully. The trouble begins when nature forces both to matter at once. That is where Planck time lives, and that is why this topic is not just about an absurdly tiny interval, but about one of the deepest unresolved problems in all of physics. To appreciate why the meeting is so difficult, it helps to remember how differently the two theories think about the world. Quantum physics describes reality in terms of states, probabilities, and measurable outcomes. It does not usually picture particles as tiny hard marbles moving along exact paths. Instead, it gives us a world where the outcomes of measurements are constrained by probabilities, where certain quantities cannot both be known with arbitrary precision, and where the act of measurement itself is woven into the story in a non-trivial way. It is a theory that has been tested with extraordinary success. It explains atoms, chemistry, semiconductors, lasers, nuclear processes, and a good portion of the technology through which modern life manages to overcomplicate itself before breakfast. At microscopic scales, quantum theory is not merely useful, it is essential. Gravity, by contrast, enters modern physics through general relativity, and general relativity does something conceptually stunning. It does not treat gravity as an ordinary force pulling objects through a fixed background. It treats gravity as geometry. Mass and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. That idea is both elegant and deeply strange. It means that space and time are not passive containers. They participate. Clocks run differently depending on gravity. Paths bend. Time dilates. The geometry of reality itself responds to what is inside it. And once again, the theory works magnificently. It explains Mercury's orbit, the bending of starlight, gravitational waves, black holes, and the expansion of the universe with spectacular accuracy. So far, so wonderful. The problem is that the two theories are built on very different conceptual foundations. Quantum theory usually assumes some kind of background structure in which physical processes unfold, even if that background is sometimes simplified. Time is often treated as a parameter against which states evolve. Space may be described in terms of coordinates or fields defined on a spacetime backdrop. General relativity, however, does not give you a fixed backdrop. The background itself is dynamical. Space-time bends, stretches, and responds to energy. In one theory, the stage is flexible and part of the play. In the other, the actors behave in ways that demand a quantum description. but the stage is often left unquantized. When these frameworks are kept in their natural territories, this tension can be managed. But once gravity becomes strong on very small scales, the difference becomes impossible to ignore. This is the key point. Most of the time, gravity is far too weak to matter in quantum experiments. If you are studying electrons in an atom, you do not need to worry about quantum fluctuations of spacetime. If you're studying planetary motion, you do not need to quantize gravity to predict orbits. Nature kindly separates the regimes for us much of the time, but not always. Near black hole singularities, in the earliest universe, and at the Planck scale, gravity is strong and quantum effects cannot be neglected. There, the theories are forced into the same room, and that is exactly where they stop speaking cleanly to each other. Planck time is significant because it is the characteristic time scale of this confrontation. It is built from the constants that belong to relativity, quantum theory, and gravity together. That tells us immediately that this is the scale where none of the theories can be safely ignored. If you go to intervals around this size, the universe demands an account in which quantum uncertainty and gravitational curvature are both present in full force. The trouble is that no complete and experimentally confirmed theory currently exists that unifies them perfectly. We have candidates, programs, deep mathematical ideas, and whole forests of papers, but not the final answer. To see why a union is so hard, it is useful to think about what quantizing gravity might mean. The other fundamental interactions in nature can be described in quantum field theory, where fields fill space and their excitations appear as particles. This framework has been extraordinarily successful for electromagnetism and the nuclear forces. It is tempting to try the same move with gravity. Treat the gravitational field quantum mechanically, allow it to have quanta, and build a theory parallel to the others. At first this seems sensible, but gravity is not just another field sitting inside spacetime. In general relativity, gravity is the geometry of spacetime itself. So quantizing gravity does not merely mean adding another quantum field to the list. It means quantizing the structure that underlies location, distance, and duration. That is a far more radical task. Imagine trying to perform ordinary quantum calculations when the notion of a fixed space-time background has itself become uncertain. Usually one assumes a geometry on which processes occur. One can then speak of trajectories, interactions, scattering, and time evolution. But if space-time is fluctuating quantum mechanically, the coordinates lose some of their familiar meaning. Distance may not be sharply defined. Duration may not be sharply defined. Even causal order may become subtle if the underlying geometry is no longer stable in the classical sense. It is hard enough to do physics in a world where particles behave strangely. It is considerably harder when the stage on which they behave is also fluctuating, and possibly not fundamental. This is why quantum gravity is not merely a technical problem. It is a conceptual one. It is not just that the mathematics gets difficult, though it certainly does, often in ways that make ordinary difficulty seem rather relaxed. It is that the categories we use to describe physical reality may need revision. What is an event if space-time itself is quantum? What is time evolution if time is not a fixed parameter? What is locality if geometry is emergent? These are not decorative philosophical questions attached to the science afterward. They sit inside the problem itself. A major source of trouble comes from infinities. When physicists tried to quantize gravity in straightforward ways similar to other quantum field theories, the calculations often produced divergences that resisted the standard techniques used to tame them elsewhere. This is one of the technical signs that gravity does not fit neatly into the same mold. It is as though the theory keeps reminding us that gravity is special, because it couples to energy in a universal way, and because energy itself shapes the background geometry. The usual methods begin to fray. That does not mean gravity cannot be quantum. Most physicists suspect it must be in some sense, because the universe does not generally tolerate one fundamental sector being exempt from quantum principles while everything else participates. But it does mean the route to a consistent theory is more subtle than simply copying the methods of other forces. Then there is the problem of time, one of the strangest features of the whole enterprise. In ordinary quantum theory, time often enters as the parameter with respect to which states change. One asks how a wave function evolves in time, but in general relativity, time is part of the dynamical geometry, not an external stage manager standing outside events with a stopwatch. When you try to combine the theories fully, this difference becomes acute. In some formulations of quantum gravity, the equations that are supposed to describe the universe do not contain time in the usual way at all. The result is deeply unsettling. At the level where gravity and quantum theory truly meet, time, the very thing we thought we were trying to understand through Planck time, may stop appearing as a basic variable in the familiar sense. That is one reason the Planck scale is so conceptually rich. It is not just where smallness becomes impressive, it is where the meaning of time itself comes under pressure. A timescale defined by the union of gravity and quantum theory leads us directly to a theory in which time may not be fundamental. The irony is almost too neat. We go looking for the smallest tick and find ourselves questioning whether the deepest layer of reality ticks at all. Black holes provide another powerful clue that quantum physics and gravity must eventually be reconciled. Classical general relativity predicts black holes with event horizons and singularities. Quantum theory, when applied near horizons, leads to effects such as black hole radiation. Suddenly gravity, thermodynamics and quantum fields are all entangled in the same problem. Black holes appear to have entropy and temperature. They radiate. They can, at least in principle, evaporate. These facts suggest that gravity participates in a deeper quantum statistical structure. They also lead to puzzles about information unitarity and what becomes of physical states when black holes evaporate. The black hole information problem is not just a niche technical puzzle. It is one of the places where the incompatibility between our two great theories becomes painfully vivid. The early universe poses a related challenge. If we run cosmic history backward, we reach states of increasing density and temperature until the known laws stop fitting together. At that stage, quantum fluctuations of the gravitational field cannot be ignored. The universe is not merely full of energetic particles. The geometry itself is part of the quantum problem. Any adequate description of the origin or earliest evolution of the cosmos therefore requires a theory of quantum gravity. Without it, one eventually reaches a limit where the equations become more like warning signs than explanations. Planck time marks the edge of that explanatory reach. Because the need is so clear, many approaches to quantum gravity have been proposed. String theory is one of the most famous. In its broadest picture, the fundamental entities are not point particles, but tiny extended objects whose different vibrational modes correspond to different particles. One of the attractive features of this framework is that gravity appears naturally within it. In a sense, it does not have to be awkwardly inserted afterward. The theory also suggests that spacetime may have more dimensions than we ordinarily perceive, and that geometry itself may emerge from deeper structures. String theory is mathematically rich and conceptually ambitious, though it remains challenging to connect definitively with experiment in the regimes where its deepest claims matter most. Another major approach is loop quantum gravity, which attempts to quantize spacetime geometry more directly. In this family of ideas, space may have a discrete structure at the smallest scales, with areas and volumes taking on quantized values. The smooth space-time of general relativity then emerges as a large-scale approximation. This picture naturally resonates with the idea that time and space may not be infinitely divisible. It treats geometry itself as something with quantum structure, rather than assuming a smooth continuum all the way down. Whether this approach yields the final story remains uncertain, but it captures one of the most intuitive responses to the quantum gravity problem. If spacetime is what gravity is made of, perhaps spacetime itself must come in quantum pieces. There are other approaches too. Some focus on causal relations as fundamental. Some pursue asymptotic safety, hoping gravity becomes well behaved at high energies through a subtle self-consistency. Some explore emergent spacetime from quantum information, where geometry is reconstructed from entanglement patterns. Others investigate holographic principles suggesting that the information content of a region may be encoded in lower dimensional terms. These ideas differ dramatically, but they all arise from the same basic necessity. Quantum physics and gravity must meet somewhere, and Planck time tells us where the meeting becomes unavoidable. It is worth emphasizing how unusual this is historically. Most successful physical theories extend previous ones by refining them, correcting them, or showing their limits. Here, however, we're not simply patching one corner of an old framework. We're confronting a conflict between two of the most successful theories ever devised. Each has passed immense numbers of tests. Each seems indispensable, yet together they are incomplete. That is part of what makes the quantum gravity problem so compelling. It is not born from failure in the ordinary sense. It is born from too much success in incompatible forms. There is also a psychological challenge in dealing with this area of physics. Human intuition is already strained by relativity alone. Time dilation, curved space-time, and the relativity of simultaneity are not exactly natural thoughts for creatures who schedule lunch and complain that the week went quickly. Quantum theory is even less intuitive. Superposition, uncertainty, entanglement, and probabilistic outcomes do not sit comfortably with everyday habits of thought. When the two theories meet, the result is not easier. It is a region where the basic grammar of reality may differ sharply from the categories we evolved to navigate gardens, weather, and social embarrassment. This does not mean it is incomprehensible in principle, but it does mean that progress may depend more on mathematical coherence than on comforting imagery. Still, the difficulty should not obscure the beauty of the situation. The Planck scale exists because the universe itself places these theories in relation. It is not an arbitrary intellectual exercise. Nature has given us a clue. By combining the fundamental constants of relativity, quantum theory, and gravity, we arrive at a scale where the conflict becomes physically meaningful. That is extraordinary. It means the deepest problem is not hidden in some purely speculative fantasy. It is etched into the structure of the constants we already know. This is also why the phrase quantum physics meets gravity has so much weight. It is not simply the meeting of two subjects from different chapters in a textbook. It is the convergence of two different visions of reality. One says the world is probabilistic, quantized in crucial respects, and fundamentally constrained in what can be jointly known. The other says the world is geometrical, dynamical in its very stage, and shaped by mass and energy through curvature. Where they meet, space-time may become quantum, time may become emergent, and the sharp distinction between background and content may collapse. Planck time is the shortest interval that reliably signals this junction. There is a tendency in popular science to present this meeting as though we are just waiting for one more clever insight, and then the curtain will rise on a final unified picture. Perhaps. But history suggests humility. The last major revolutions in physics required not just smarter calculations, but new conceptual frameworks that changed what counted as obvious. Quantum gravity may demand the same. It may ask us to give up the assumption that time is fundamental, that space is continuous, that causality is primitive, or that geometry is basic. Or it may reveal a synthesis none of our current instincts properly anticipates. The point is that when quantum physics meets gravity, the result may not be a compromise between old ideas so much as a transformation of them. Planck time is therefore best understood as a signpost toward that transformation. It tells us that there is a natural scale where all the comforting separations fail. The microscopic cannot ignore gravity. The geometric cannot ignore quantum uncertainty. The background cannot remain unexamined. The very possibility of measuring duration becomes entangled with the nature of space-time itself. That is a lot to ask of a concept associated with the smallest unit of time, but the universe rarely worries about assigning more meaning to a scale than seems politely necessary. And once quantum physics and gravity are forced together, another question becomes unavoidable. If Planck time marks the threshold where our theories meet and fail, then what can actually happen within such an interval? Can events occur in any ordinary sense during the smallest meaningful time scale? Or does the idea of happening itself become unstable there? That question is where the story naturally goes next. Because once the deepest theories collide, the meaning of process, change, and temporal order becomes harder to take for granted. One of the strangest questions raised by Planck time is also one of the simplest to ask. Can anything actually happen within it? At first glance, the answer seems obvious. Of course, something could happen in a very short interval. After all, things happen in fractions of a second all the time. Light travels, particles interact, atoms vibrate, signals move, fields fluctuate. Physics is full of fast processes, so it is natural to assume that Planck time is simply the shortest version of a familiar situation, the tiniest available slice of duration in which one could still place an event. But the more carefully you examine the question, the more unstable the word happen begins to feel. That is because Planck time is not merely a very small interval on an otherwise ordinary clock. It is the scale where the concepts needed to define events, durations, locations, and causal sequence may themselves become unreliable. This is why the question is so revealing. It sounds like a matter of speed, but it is really a matter of meaning. To ask whether anything can happen within Planck time, we first need to know what counts as a happening. In everyday life, that seems easy. A glass falls, a sentence is spoken, a kettle boils eventually with an air of reluctant cooperation. These are happenings because they involve change over time. One state gives way to another. There is a before and an after. A process unfolds. Physics normally formalizes this by describing systems that evolve. A particle moves, a field oscillates, a wave spreads, a clock ticks. Even if the timescales are tiny, the structure remains familiar. There is temporal order and physical change. But Planck time is precisely the scale at which the smooth framework supporting such descriptions becomes questionable. If time itself is no longer reliably continuous, if spacetime geometry is fluctuating, if the distinction between one moment and the next cannot be operationally defined with our current theories, then the ordinary meaning of happen may begin to dissolve. A happening assumes an interval within which change can be tracked. It assumes some stable notion of sequence. It assumes that we can identify one state and then another state later. At the Planck scale, each of those assumptions comes under pressure. The first temptation is to picture Planck time as a minimal frame in a cosmic film. On this view, reality updates once every Planck time, and anything that happens must do so from one frame to the next. This is a very popular mental image because it is simple and intuitive. It treats Planck time like the shortest tick of a universal clock, but there are two problems with it. The first is that present physics does not actually establish that the universe works like a frame-based animation. The second is that even if time were discrete at the deepest level, that would not automatically mean the world advances in a sequence of little snapshots with pauses in between. That picture owes more to our experience of digital media than to any confirmed theory of quantum gravity. So the cautious answer is that we do not know whether reality advances in discrete temporal steps. What we do know is that Planck time marks the scale below which our current theories stop giving a meaningful account of shorter intervals. That means if something does happen within Planck time, it may not be describable as a process unfolding through a series of subintervals in the ordinary way, because those subintervals may not be physically meaningful. The usual structure of process could break down. This can seem slippery, but the slipperiness is honest. Suppose you ask whether anything can happen in a single mathematical point of time in classical physics. The answer is already a bit subtle. A process usually requires an interval, however small. A point in time is not itself a duration over which change can unfold. It is more like a marker. Yet physics often describes a system as having properties at an instant, and then changing across neighbouring instants. Now imagine pushing that logic down to the Planck scale. If Planck time is indeed the smallest meaningful interval, then there may be no physically significant smaller neighbourhood around it in which to define finer stages of a process. In that sense, asking what happens within Planck time may be a bit like asking what motion occurs within a single indivisible step, assuming indivisibility is real. The question may be trying to subdivide something that no longer supports subdivision. There is also the measurement problem, in the broad practical sense rather than the technical interpretation-heavy sense. For anything to count as happening physically, one would like, at least in principle, to be able to distinguish different states or outcomes. But to resolve intervals as small as Planck time would require energies and localization so extreme that our ordinary measuring concepts collapse into the quantum gravity problem. The act of probing such an interval would disturb the geometry of spacetime itself, so even if there is a meaningful physical answer to what happens within Planck time, it may not be the sort of answer that can be framed in terms of an observer cleanly watching a process unfold. The observational structure that underlies ordinary talk of events may no longer apply. This pushes us toward a more careful distinction between change and description. Something might be real without being describable in classical temporal language. A deeper theory of quantum gravity may contain structures, transitions, or relations that later appear to us as events in time, even if at the fundamental level they are not organized by time in the usual sense. In that case, asking whether anything happens within Planck time could be a bit like asking whether temperature occurs inside a single molecule. The language is not entirely meaningless, but it misses the level at which the concept properly applies. Temperature emerges from large numbers of particles. Perhaps happenings in time emerge from deeper relations that only become process-like at larger scales. This is one of the reasons some physicists suspect that time is emergent rather than fundamental. If time is emergent, then the deepest level of reality may not be made of things happening in time at all. Instead, it may be made of relations, structures, amplitudes, or transitions that only produce temporal sequence when viewed at a coarse enough scale. In that picture, Planck time is not a little box in which events occur. It is the threshold below which the language of occurrence itself must be reformulated. That possibility is unsettling because event language is central to how we think. We naturally ask what happened first, what changed, what caused what. These questions are the grammar of common sense, but common sense evolved for creatures dealing with objects, meals, weather, and deadlines, not for analysing the deep structure of quantum spacetime. Physics has repeatedly forced us to abandon familiar grammar when it became misleading. The Earth is not stationary even though it feels stationary. Simultaneity is not absolute even though daily life treats it as absolute. Matter is not solid in the way it seems to be. Time itself may not be fundamental in the way it feels. Against that background, the idea that happening might not be primitive is radical but not absurd. Still, one should not conclude too quickly that nothing can happen at the Planck scale. That would be overstating the case in the opposite direction. The problem is not that Planck time is a frozen interval in which all physics halts politely. The problem is that our current concepts of process may not map cleanly onto that scale. In many theoretical approaches, there is still some kind of dynamical structure. Quantum states may evolve, causal relations may be generated, spin networks may transform, strings may interact, or information theoretic patterns may reconfigure. The deeper theory, whatever it turns out to be, is unlikely to be a picture of eternal stillness. But the things occurring there may not be happenings in the everyday temporal sense. They may be more primitive than events, with ordinary events emerging only later as an effective description. This is a useful point to dwell on because it prevents a common misunderstanding. When physicists say that intervals shorter than Planck time may not be meaningful, they are not saying that the universe goes blank there. They are saying that our familiar descriptors of time and change cease to be reliable. That is a very different claim. A map can fail to represent a region without the region being empty. Sometimes the region is more complicated than the map. The Planck scale may be exactly such a case. Another way to approach the question is through causality. To say that something happens usually implies some ordering. A happened before B, or B resulted from A. But if spacetime itself is fluctuating or emergent, causal order may no longer be sharply defined at the smallest scales. Some approaches to quantum gravity suggest that the causal structure of the universe is itself fundamental and perhaps discrete. Others suggest that causality may become blurred in quantum regimes or only stabilize macroscopically. If causal order is not fully settled at the Planck scale, then asking whether anything happens within Planck time becomes even trickier. A happening without a definite place in a before and after structure is already stretching the familiar concept quite hard. There is an interesting parallel here with quantum processes more generally. Even away from gravity, quantum theory does not always support the neat classical picture of a system occupying one state and then another in a clear, observer-independent sequence. Superpositions, interference, and measurement issues already complicate what it means to say that something happened in a definite way. Add gravity to the mix, and the complication deepens. It may no longer be enough to ask whether an event occurred at a certain time. One may need to ask what structures in the deeper theory later appear as localized events when a classical space-time description emerges. The idea of a process requiring time also deserves scrutiny. In ordinary thought, yes, a process needs duration, but if time is emergent, then process might be fundamental while time is not. That sounds backwards, but it is not impossible. One can imagine a deeper level of relational change or structural reconfiguration, from which temporal ordering emerges only in a coarse-grained sense. In that picture, something can certainly happen beneath the Planck scale, in the underlying theory, but not as a process unfolding within smaller and smaller temporal slices. Instead, temporal slices themselves are secondary. The fundamental happening is not in time. Time is one of its large-scale appearances. This is difficult to picture, and that is fine. The goal is not to form a cozy image, but to understand the logical possibilities forced upon us by the breakdown of current theory. We are dealing with a scale where familiar categories may not survive intact. Physics does not owe us an intuitive cartoon. It owes us conceptual discipline and eventually predictive power. It is also worth considering the possibility that Planck time is not a hard minimum in a literal ontological sense, but rather a sign of present theoretical inadequacy. If that is true, then perhaps shorter intervals are meaningful after all, but only within a future theory that reconceives space-time in some unexpected way. In that case, asking whether anything can happen within Planck time would be like asking an early scientist whether anything can happen inside an atom. The best available theory might have implied a limit, while a deeper theory later revealed internal structure. This possibility remains open, and it is one reason careful physicists resist making definitive metaphysical claims based solely on the Planck scale. Nature has surprised us before. Even so, there is a difference between saying we might one day have a better description and saying our current description already licenses confident answers. It does not. At present, the most responsible position is that Planck time marks a threshold below which our ordinary notion of happening becomes physically uncertain. That is not ignorance in the lazy sense. It is a precise acknowledgement of where theory reaches its limit. One can perhaps make the issue more tangible with a comparison to motion in a digital simulation. If a simulation updates in discrete steps, then asking what happens within a single update cycle may be misguided because the model has no substructure there. Motion exists across updates, not within one indivisible update. But now imagine a more subtle case where you're not even sure whether the simulation is discrete, continuous, or something stranger whose large-scale behaviour merely looks continuous. That is closer to our situation with Planck time. We can see enough to suspect that the ordinary continuum picture is strained, but not enough to assert with certainty that reality is a simple sequence of indivisible updates. There is also the question of whether a Planck interval could contain multiple distinguishable states. If time is fundamentally discrete, and Planck time is the minimum interval, perhaps one could still imagine a system changing from one configuration to another across that step. But to say that with confidence, one would need a theory specifying how states are defined at that level and how transitions occur. We do not yet have such a complete theory, so the statement remains speculative. Some candidate frameworks imply such transitions, but none is presently established as the final description of nature. In some approaches, the deeper reality is less about states at times and more about amplitudes connecting boundary conditions, or networks related by transformations, or histories weighted in a path like formalism. In these formulations, the question "can anything happen?" within Planck time may be partly replaced by a different question. What structures or relations in the fundamental theory give rise to the appearance of temporal evolution at scales larger than the Planck regime? That is a more modern and probably more fruitful way to think about it. It shifts attention from microscopic events inside a tiny box of time to the origin of event structure itself. This may seem like an evasive move, but it's actually a sign of scientific maturity. Good science often progresses by discovering that an old question was posed in the wrong conceptual language. Asking what the ether is made of turned out not to be the right question once the ether itself was abandoned. Asking what is happening within Planck time may similarly be too attached to a classical temporal framework that the deeper theory does not share. The replacement question may concern how classical time emerges, how causal order stabilizes, or how measurable processes become possible at scales larger than the Planck domain. Still, one cannot help but feel the pull of the original question, because it gets at something deeply human. We live by happenings. The world arrives for us as sequence, memory, anticipation, action, consequence. To discover that at the smallest scale the notion of happening may dissolve into something more primitive is intellectually unsettling. It suggests that the flowing world of experience is not the deepest layer, but a large-scale organization of something more abstract and less story-friendly. That is a major philosophical shift hiding inside a deceptively simple physical question. At the same time, there is a certain beauty in it. The question, "can anything happen within Planck time?" turns out not to be answered by a simple yes or no, but by a revelation. It reveals that happen is not as basic as it seems. It depends on time being meaningful, on causality being stable, on space-time geometry being coherent enough to support distinguishable states and ordered change. At the Planck scale, all of those supports may become unstable together. So the smallest interval of time is not merely small. It is the point where our very idea of process begins to fray. If one wants the shortest honest answer, it is this. Something may occur at the Planck scale, but what occurs there may not be describable as an event unfolding within time in the ordinary sense. Our current theories do not allow us to say more with confidence. The interval is too deep in the quantum gravity regime. It is where the distinction between duration and structure, between process and relation, between happening and being, may need to be rethought entirely. And that naturally leads us onward, because if our familiar language of happening begins to fail at Planck time, then the next question is not just what can occur there, but whether the very concepts we use to measure and describe reality remain meaningful at all. In other words, once the smallest tick no longer behaves like an ordinary interval, we are pushed directly toward the limits of measurement, and perhaps even the limits of meaning itself. When we arrive at Planck time, we do not simply reach a tiny unit that is difficult to measure. We arrive at a scale where the whole idea of measurement starts becoming uncertain in a deeper way, and along with it, the meaning of the distinctions we are trying to make. That is why this stage of the subject matters so much. Up to this point, we have been able to speak about Planck time as a threshold, a natural scale, a boundary where gravity and quantum theory both demand attention. But now we have to ask something even more unsettling. What does it mean to measure anything at that scale? And if we cannot measure it even in principle, what exactly are we claiming when we speak about it at all? This is not just a technical concern. In physics, measurement is not an afterthought. It is built into the structure of the science. Physics does not merely invent concepts and admire them from a distance. It asks how those concepts connect to operations, observations, devices, records, comparisons, and outcomes. A length is meaningful because in principle it can be related to some measurement procedure. A duration is meaningful because in principle clocks or processes can distinguish it. An energy is meaningful because it affects systems in measurable ways. The deeper physics goes, the more important this becomes, because the line between a physically meaningful distinction and a mathematically possible distinction is not always the same. At everyday scales, this difference barely troubles us. We speak of seconds, meters, temperatures, masses, and fields with enormous practical confidence. We can build instruments, repeat experiments, calibrate results, and agree on what is being measured. Even in quantum physics, where measurement becomes subtle and sometimes philosophically inconvenient, the theory still connects to definite outcomes in laboratories. There are probabilities, detection events, spectra, interference patterns, counts. However strange the underlying description becomes, it still meets the world in a measurable way. At the Planck scale, by contrast, that contact starts to fray. The problem is not merely that we lack better equipment. The problem is that the conditions required to measure such scales appear to undermine the very framework in which measurement makes sense. To see this clearly, it helps to ask what a measurement of a very small interval of time would require. A clock, at any level, is a system that changes in a regular enough way to let us mark intervals. For ordinary purposes, a pendulum can serve. For greater precision, one uses quartz vibrations or atomic transitions. If you want to measure shorter and shorter intervals, you need faster and more localized processes. You need higher frequencies, shorter wavelengths, more concentrated energies. This is already familiar from much of modern physics. To resolve finer structure, you generally need more energetic probes. But this road does not continue indefinitely in a simple way. The deeper you go, the more energy you must concentrate into smaller regions over shorter durations. Quantum theory tells you that such concentration cannot be treated passively. The probe affects the system. Gravity tells you that energy is not merely an input to the measurement, but something that curves space-time itself. So at sufficiently extreme scales, trying to measure a tiny interval does not just illuminate the interval, it distorts the stage on which the interval is defined. The geometry you hope to use as a stable backdrop becomes part of the disturbance. Push far enough, and the attempt to localize a moment with greater and greater precision risks generating conditions so extreme that the region may effectively hide behind its own gravitational effects. This is one of the deepest reasons Planck time is treated as a limit of meaning rather than just a limit of convenience. If no physically possible measurement can distinguish intervals shorter than a certain scale without destroying the assumptions needed for the distinction, then the question of whether such intervals exist in the physically relevant sense becomes delicate. It is not necessarily meaningless in pure mathematics or speculative metaphysics, but physics asks a stricter question. Does the distinction correspond to anything that can, even in principle, be operationally defined within nature? If the answer is no, then the distinction may not belong to physical reality in the way familiar measurable quantities do. This is where the phrase limits of meaning becomes important. It does not mean language stops functioning, or that the universe turns mystical in some vague dramatic sense. It means that some concepts derive their meaning from the role they play in measurement, observation, and lawful description. If that role breaks down, the concept may stop applying in the ordinary physical way. This happens in other areas too, though usually less dramatically. Asking for the exact position of a classical point inside a quantum wave packet can become misleading if the underlying state does not support that classical notion cleanly. Asking for the temperature of a single fundamental particle is not usually meaningful in the same sense that the temperature of a gas is. The concept has drifted outside its proper domain. At the Planck scale, something similar may happen with time itself. It is worth noticing how unusual this is for our intuition. Time feels so basic that it seems immune to such scrutiny. We can imagine not knowing the exact age of a star or the exact duration of a chemical step, but it is harder to imagine time itself losing operational meaning below a certain threshold. Yet that may be exactly what nature is telling us. The continuous, measurable flow we inhabit may not be available all the way down, not because reality ends there, but because our concept of time as a measurable interval may be tied to a level of structure that only becomes stable above the Planck regime. This introduces a subtle but crucial distinction between what exists and what can be meaningfully described. A deeper level of reality may well underlie space-time. Something may be there, some structure, relation, dynamics, or quantum order. But if the language of time intervals is only emergent, then speaking of that deeper level in terms of smaller and smaller durations may be like describing an orchestra in terms of the temperature of each note. The words are familiar, but the fit is poor. The limitation is not necessarily in reality. It may be in the applicability of the concept. Physics has encountered this type of shift before. In classical mechanics, one can imagine exact trajectories for particles with exact positions and momenta at every moment. Quantum mechanics replaced that picture with a framework where such exact simultaneous specification is not physically available. It did not abolish reality. It changed the meaning of physical description. In thermodynamics, one can describe temperature and pressure without referring to molecules, but statistical mechanics later showed that these are collective emergent quantities. Again, the concepts were not false. They had a domain. The Planck scale may force a similar reclassification for time and space-time themselves. They may be real and indispensable at the level where we live and experiment, yet not fundamental in the ultimate description. There is also a logical temptation one must resist here. When people hear that something cannot be measured, they often leap to one of two extremes. Either they conclude it does not exist at all, or they conclude it exists in some mysterious way forever beyond science. Both reactions are too quick. The more disciplined conclusion is that our present framework does not support a physically meaningful distinction there. That leaves room for future theory to reframe the issue. It also leaves room for deeper structures that are real, but not describable in current terms. Science progresses precisely by learning to distinguish between impossible, unmeasurable within a given framework, and not yet correctly conceptualized. Still, even this cautious position has real bite. If intervals below Planck time cannot be measured or distinguished in principle using any physically possible procedure consistent with our best theories, then it is not clear what would make one such interval different from another in physical practice. Distinctions without possible consequences are suspect in physics. That does not mean physicists are crude verificationists who deny the unseen. Far from it. Science routinely posits things not directly observable, but those posits earn their keep by entering into explanatory and predictive structures that connect back to measurable phenomena. If sub-plankian distinctions can never connect in that way, their physical status becomes questionable. This is why Planck time is not just about the smallness of the universe, but about the architecture of physical thought. It forces us to ask how concepts acquire meaning in physics. Is meaning tied only to measurement? Is it tied to role in theory? Is a quantity meaningful if it is indispensable to a successful deeper framework, even if not directly measurable? Physicists do not all answer these questions the same way, but the Planck scale makes them impossible to ignore. A concept as basic as time is suddenly dragged into the same sort of scrutiny once reserved for subtler theoretical entities. One of the more interesting consequences of this is that the Planck scale becomes a meeting place not only for physics but for philosophy of physics. Questions that seem abstract in calmer contexts become unavoidable here. What counts as an event? What makes a distinction physically real? Is space-time an object, a relation, an emergent structure, or a bookkeeping device of extraordinary success? Can a theory describe a regime in which its own background concepts no longer apply? These are not optional reflections tacked on after the equations. They arise because the equations themselves reach a boundary and force us to examine what their terms mean. Consider again the ordinary notion of a clock. A clock requires repeatable structure. It requires a system that changes in a regular way against some background of time. But if time is not fundamental, then clocks do not measure an underlying independent river. They participate in an emergent order that only appears at scales where regularity and temporal comparison are meaningful. At that point, asking for a clock that measures sub-plankian durations may be asking for a device that presupposes the very structure whose emergence is in question. The request becomes circular. It is like asking for a ruler made out of the thing whose existence you are trying to establish while that thing remains undefined. This is one reason the Planck scale can feel almost self-sealing. Every attempt to dig beneath it using familiar tools runs into the fact that the tools themselves depend on the larger scale structure one is trying to go beyond. Measurement assumes spacetime coherence, localization assumes geometric meaning, duration assumes stable temporal ordering. At the Planck threshold, all of that is unstable. The result is not that nature has hidden a neat little secret behind a curtain. It is that the curtain may itself be woven out of the concepts we are trying to carry through it. That is where the limits of meaning become especially sharp. Not all questions remain well formed when carried across every scale. Science often advances by discovering which questions survive translation into deeper theory, and which were artifacts of the earlier framework. If spacetime is emergent, then asking exactly what happened at a sub-Planckian time may be like asking which side of a rainbow a molecule belongs to. The question feels concrete only because it borrows the grammar of a higher level phenomenon. At the deeper level, the categories no longer line up. This does not mean one must become pessimistic or vague. On the contrary, the limit of meaning is often the starting point for better theory. When classical trajectories stopped making full sense in atomic systems, quantum mechanics did not simply shrug, it rebuilt the framework. When absolute simultaneity failed, relativity replaced it with a richer structure. In the same spirit, the Planck scale may mark the point where concepts like time, distance, and event must be reconstructed from deeper principles rather than assumed from the start. The recognition of a limit is not the end of science. It is often the point where science becomes more precise about what it needs next. There is a practical side to this too. Even though we cannot directly probe the Planck regime, the limits we infer there can still shape observable physics. Black holes, early universe cosmology, horizon thermodynamics, and quantum information puzzles may all carry signatures of how nature handles the boundary between measurable space-time and its deeper substrate. So the fact that meaning becomes subtle at the Planck scale does not imprison the topic in abstraction. The challenge is to find indirect routes, conceptual and empirical, through which the deeper structure reveals itself in larger scale phenomena. And perhaps that is what makes this area so compelling. We are not dealing with ignorance born from lack of interest or effort. We are dealing with a genuinely profound boundary where the universe seems to tell us that the familiar language of physics, so successful across enormous ranges, may itself be emergent and approximate. The limits of measurement become the limits of our present ontology. We do not just hit a practical wall, we hit a wall built from the possible meanings of our concepts. This should not be confused with defeat. There is a difference between saying we do not know and saying nothing can be known. The Planck scale supports the first claim strongly, but not the second. We do not yet know how to describe the deep structure beneath measurable space-time. But the boundary itself teaches us something. It teaches us that measurement is not external to theory. It teaches us that physical meaning depends on the conditions under which distinctions can be made. And it teaches us that time, despite its familiarity, may be no more fundamental than the other large-scale features of reality that once seemed beyond question. There is also a rather elegant humility in this. Human beings often imagine that by making instruments finer and theories cleverer, we can keep peeling the universe like an onion forever, with every layer revealing just a smaller version of the previous one. The Planck scale suggests the onion may not behave so obligingly. At some point, the very act of peeling changes the object. At some depth, the language of layers may stop working. The structure may no longer support the assumptions built into the metaphor. That is not disappointing. It is, in its own way, a sign that reality is more original than our habits of thought. If one were to summarize the issue as simply as possible, it would be this. Planck time marks a regime where the attempt to measure shorter intervals runs into a fundamental conflict between quantum uncertainty and gravitational back reaction. Because of that conflict, intervals below this scale may not be physically distinguishable in any operational sense, and if they are not distinguishable, then the meaning of talking about them in the ordinary language of time becomes questionable. The limit is therefore not just on measurement in a technical sense, but on the applicability of the concept itself. That is a serious conclusion, and it leads us naturally to more extreme physical settings, where these questions become especially vivid. If the Planck scale marks the boundary of measurable space-time, then black holes and the most violent cosmic conditions are exactly the places where that boundary becomes more than a philosophical concern. They become laboratories, at least in principle, for the deep relationship between Planck time, gravity, and the structure of the universe. And so the next part of the story turns toward those extremes, where the smallest meaningful interval of time meets the most intense objects and events known to physics. If Planck time is the scale where our ordinary ideas about duration begin to fail, then black holes are among the most natural places to see why. They are not merely strange objects sitting somewhere at the edge of astronomy, looking theatrical and swallowing metaphors for a living. They are places where gravity becomes so strong that the structure of space-time itself is pushed toward extremes, and whenever space-time is pushed toward extremes, the Planck scale starts hovering in the background like an unsmiling examiner waiting for us to show our work. This is why black holes and Planck time belong in the same conversation. The smallest meaningful interval of time becomes especially important precisely where the universe bends time and space hardest. To begin gently, it helps to recall what a black hole is in the framework of general relativity. A black hole is not a cosmic vacuum cleaner roaming the universe with malicious intent. It is a region where matter or energy has been compressed so strongly that gravity curves space-time in a way that creates an event horizon, a boundary beyond which signals cannot escape back out to distant observers. Outside the horizon, gravity may be intense but still describable in the ordinary language of curved space-time. Inside, at least in classical theory, the geometry continues inward toward a singularity, a place where curvature grows without bound, and the theory itself effectively confesses that it has reached the end of its competence. That last part is what matters most for us. Singularities are not best understood as neat physical objects already explained by theory. They are warning labels. They tell us that general relativity, magnificent though it is, has been pushed into a regime where it no longer gives a complete account. And what regime is that? A regime of enormous density, immense curvature, compressed scales, and extreme gravity. In other words, exactly the kind of regime where Planck scale physics should become unavoidable. So black holes are not just dramatic astrophysical curiosities, they are places where the need for quantum gravity becomes impossible to ignore. This connection shows up in several ways. The first is straightforward. As matter collapses inward under gravity, the densities and curvatures involved grow. If one follows the classical equations all the way down, one is led toward a region where distances and durations become so tiny that the Planck scale is the natural reference point. Once that happens, Planck time stops being an abstract threshold and becomes the scale at which the current theory is telling us it can no longer go further alone. Somewhere near that domain, the smooth classical picture of space-time should give way to whatever deeper quantum gravitational structure actually governs reality. So when we ask what happens inside black holes, especially near the classical singularity, we're really asking what happens when space-time is pushed to Planckian extremes. Does time remain continuous there? Does space remain smooth? Does the singularity truly exist? or is it replaced by some deeper quantum structure? Does collapse, stop, bounce, smear out, or reorganize into something our current theories cannot yet fully express? These are not decorative speculations. They are precisely the sorts of questions Planck time forces upon us whenever gravity becomes violent enough. Now, black holes also change the way time behaves, even before we get anywhere near such ultimate depths. One of the most famous features of relativity is gravitational time dilation. Clocks closer to a strong gravitational field tick more slowly relative to clocks farther away. Near a black hole, this effect becomes extreme. To a distant observer, processes close to the event horizon appear drastically slowed. Matter falling inward seems to linger, fading and reddening, never quite crossing the horizon in finite distant observer time in the simplest classical description. From the perspective of the falling observer, however, the crossing happens in finite proper time. This difference is a classic reminder that time in relativity is not universal. It depends on motion and gravity. That alone would make black holes interesting for any discussion of time. But Planck time deepens the issue because it asks what happens when these relativistic distortions are carried toward the limits of meaningful duration. If one observer sees infall stretched enormously while another experiences finite time on the way inward, and if the internal geometry drives curvature toward the Planck scale, then the simple idea of a shared temporal story begins to break apart. Black holes are not just places where clocks disagree by a little. They are places where the concept of time can become so observer-dependent and so entangled with geometry that the usual narrative of events becomes deeply strained. This already suggests something important. Planck time does not become relevant in black holes merely because there are short durations involved. It becomes relevant because the very structure that supports time is under extreme gravitational stress. A stopwatch in a laboratory and a clock dragged toward a black hole horizon are not confronting the same conceptual problem. In the laboratory, time is being measured within a stable space-time background. Near a black hole, time is itself caught inside a geometry so distorted that the transition from ordinary description to Planckian uncertainty becomes a live issue. The situation becomes even more interesting when quantum theory enters. Classical black holes were once thought to be purely absorbing objects, simple in a somewhat terrifying way, but quantum field theory and curved space-time change that picture. Black holes are not entirely black. They radiate. This is one of the great surprises of modern physics. Near the event horizon, quantum effects lead to the production of radiation associated with the black hole. As a result, black holes can lose mass over time and in principle evaporate. This discovery tied together gravity, quantum theory, thermodynamics, and information in one profoundly uncomfortable package. Why uncomfortable? Because once black holes radiate, they acquire temperature and entropy. They stop being just geometric pits in space-time and start behaving like thermodynamic systems with microscopic information content. That immediately raises a question. What are the microscopic degrees of freedom underlying this entropy? In ordinary thermodynamics, entropy reflects the number of microscopic configurations compatible with a macroscopic state. For black holes, what are those configurations? If the entropy is real, and it appears to be, then gravity must somehow hide a microscopic structure. And wherever microscopic structure underlies geometry and thermodynamics, the Planck scale is usually nearby. This is one reason black hole physics became one of the central arenas for thinking about quantum gravity. The horizon area, the entropy, the temperature, the evaporation process, and the information puzzle all suggest that space-time itself has deeper layers than classical general relativity reveals. Planck time matters here because evaporation, information release, and near-horizon quantum processes eventually force us to confront the scale at which the smooth, classical background breaks down. The smallest meaningful duration is not merely a curiosity. It may be bound up with how black holes store and process information at the most fundamental level. The black hole information problem makes this tension especially sharp. In ordinary quantum theory, information is not supposed to vanish from the fundamental description. The evolution of states preserves it in a specific formal sense. But if a black hole forms from matter, carrying information, and then evaporates away into featureless thermal radiation, where does that information go? Has it been destroyed, hidden, scrambled, released in a subtle way? Does it remain in some remnant? Does the horizon encode it holographically? The tension here is not an optional detail. It is a sign that our understanding of the marriage between quantum theory and gravity remains incomplete. The reason Planck time lurks behind all this is that whatever finally resolves the information problem will almost certainly involve the deep quantum structure of spacetime. The answer may depend on what happens near the Planck scale at horizons, in the interior, or in the final stages of evaporation. The smallest meaningful interval of time may influence how one even defines the evolution of a black hole spacetime, how information is encoded, and what counts as an event in a geometry that is not classically smooth all the way down. There is also the issue of the final stage of evaporation. Large black holes evaporate extraordinarily slowly, so slowly that the process is leisurely beyond anything human timescales can seriously appreciate. But as a black hole loses mass, its temperature rises. In the late stages, the physics becomes more extreme. Eventually one expects the system to enter a regime where the remaining mass, size and curvature approach the Planck scale. At that point, the semi-classical treatment used for much of the evaporation process ceases to be reliable. One is again pushed directly into the domain where Planck time, Planck length and quantum gravity become central. Does the black hole disappear entirely, leave behind a remnant, release a final burst, transition into something else? Current theory does not settle the matter. The Planck regime takes over, and our best existing framework stops short of a final answer. This is a recurring pattern. Black holes begin as astrophysical objects, but follow their logic far enough, and they become laboratories for the deepest questions about the nature of time, geometry, and information. Planck time keeps reappearing because every route inward or forward in their most extreme behaviour ends at scales where our ordinary description of duration and space-time fails. Now, black holes are not the only cosmic extremes relevant here. The early universe itself is perhaps the grandest example. We have already touched on the universe younger than a Planck moment, but in the present context it is useful to place that beginning alongside black holes as part of the same family of problems. Both involve gravity-driven extremes. Both involve conditions where density, temperature and curvature reach the limits of known theory. Both point towards singular behaviour in classical descriptions. Both demand some quantum gravitational completion. In that sense, the inside of a black hole and the beginning of the universe are not identical, but they are close conceptual cousins. Each is a region where Planck scale physics becomes unavoidable because space-time is being pushed beyond the classical domain. This symmetry has inspired many theoretical ideas. Some suggest that singularities are never truly reached, because quantum gravity smooths them out. In cosmology, that could mean the Big Bang singularity is replaced by a bounce or transition from an earlier phase. In black holes, it could mean the interior avoids an actual singular endpoint, and instead undergoes some other kind of transformation. The details vary widely across approaches, but the common thread is clear. Classical singularities are likely signs of theoretical incompleteness, and Planck scale physics is the likely arena in which the completion occurs. There is something rather elegant about that. The largest structures and most violent events in the universe end up forcing us to care about the smallest meaningful units. Galaxies, stars, collapse, cosmic origin, black holes, all these grand themes ultimately drive us toward Planck time. It is one of the recurring lessons of physics that the very large and the very small are not separate kingdoms. They are entangled more intimately than common sense would guess. The edge of a black hole and the earliest universe both reach down toward the same fundamental scale where our concepts begin to falter. Another cosmic extreme that brings Planck time into view is the possibility of primordial gravitational phenomena from the early universe. If quantum gravity effects left subtle imprints in the earliest cosmic structure, those traces might survive in patterns of gravitational behaviour, high-energy relics, or subtle signatures in the large-scale arrangement of matter and radiation. At present, none of this has yielded a clean direct measurement of Planck-scale physics, but the principle remains important. Extreme cosmic environments may be our best route to learning about the smallest scales, because we cannot build them on Earth in any straightforward way without greatly upsetting the funding committees of the world. There is also a more conceptual extreme worth mentioning, namely the edge of causal explanation itself. Black holes create horizons, and horizons limit what different observers can know and compare. This matters for time because it shows that temporal description is not just about the ticking of clocks, but about the accessibility of events and the causal structure connecting them. Near horizons, those structures become subtle. Information may be hidden. Sequences may look radically different from different observational standpoints. Once again, this means that the significance of Planck time is not only about tiny durations, it is about the point where duration, geometry, causality and information all become inseparable. That intertwining has led to some of the most striking ideas in modern theoretical physics. Holographic principles, for example, suggest that the information content of a region of space may be encoded in a lower dimensional description associated with its boundary. This is a remarkable shift in perspective, and black holes played a major role in motivating it. If something like holography is fundamental, then the deep structure of spacetime may not be what it seems. Geometry itself may be emergent from more basic informational or quantum relationships. If so, Planck time would again mark not merely a small interval, but a threshold beneath which the familiar spacetime picture must be replaced by something more abstract. The same applies to attempts to understand black hole interiors through quantum entanglement and information theoretic ideas. Increasingly, physicists suspect that spacetime geometry and quantum entanglement are deeply related. In some lines of thought, connectivity in spacetime may actually arise from entanglement structure. If that is true, then the cosmic extremes of black holes become especially valuable because they are places where entanglement, horizon, physics, and geometry all come together in a form dramatic enough to reveal the underlying architecture. And whenever that architecture is probed at its deepest level, the Planck scale waits in the wings. There is a nice irony in this. Black holes look from afar like monuments to silence. They hide information, trap light, and seem to swallow every simple question we ask of them. Yet in modern physics, they have become among the loudest objects conceptually. They keep telling us that our understanding of space-time is incomplete. They keep forcing quantum theory and gravity into the same frame. They keep dragging Planck-scale questions out of the safe realm of abstract theory and into the heart of astrophysics and cosmology. And perhaps that is the best way to understand why Planck time belongs here. It is not because anyone expects to watch a black hole tick in Planck-sized increments. It is because black holes are among the few natural settings where the limitations signalled by Planck time become unavoidable. Their horizons, interiors, thermodynamics, and final evaporation all lead us toward the same boundary. The smallest meaningful interval of time becomes physically relevant wherever the geometry of the universe is bent, compressed, and heated beyond the point where classical spacetime can survive unchanged. The same is true, in a broader sense, of all cosmic extremes. The earliest universe, the densest collapse, the strongest gravitational distortions, the hottest and most violent regimes, all of them drive physics toward the Planck domain. They are reminders that the universe has no interest in keeping the deepest scales politely separated from the grandest structures. The fate of stars, the origin of the cosmos, and the structure of time itself are entangled more intimately than one would ever suspect from the experience of waiting for a kettle or watching the evening sky darken over a quiet street. So by the time we have passed through black holes and cosmic extremes, Planck time begins to look less like a mere unit and more like a crossroads. It stands at the meeting point of collapse and origin, geometry and quantum uncertainty, thermodynamics and information, causality and measurement. It is the scale the universe keeps returning us to whenever we ask what happens when known physics is stretched to its furthest limits. And once that picture settles in, the final step becomes unavoidable. If the smallest meaningful interval appears not only in the deepest theory, but also at the edges of black holes, the beginning of the cosmos, and the limits of measurement, then we have to ask what all of this means for the way we understand reality as a whole. Because by now, Planck time is no longer just a scientific fact to be defined. It has become a way of asking the biggest possible questions through the smallest possible window. By the time we arrive here, Planck time no longer feels like a mere number tucked away in the far corner of theoretical physics. It has become something much more interesting. It began as the smallest meaningful interval of time, or at least the interval below which our present theories stop speaking clearly. But along the way it opened into questions about the beginning of the universe, the fate of black holes, the structure of space-time, the limits of measurement, and the uneasy relationship between quantum theory and gravity. That is one of the lovely peculiarities of physics. You start with something extremely small, and before long you are talking about everything. There is a certain pattern to the way deep science works. The closer you look at the foundations, the less isolated any concept remains. Time is not just time, it is tied to space. Space is not just emptiness, it is tied to geometry. Geometry is not just shape, it is tied to matter and energy. Matter and energy are not just stuff, they are tied to quantum fields, uncertainty and information. And when all of these threads are pulled tightly enough, they seem to converge around the Planck scale. That is why Planck time matters. Not because it is a fun way to impress someone by saying the universe has a very tiny stopwatch hidden in its pocket, but because it marks the place where many of our most successful ideas reach their limit together. That limit is not a failure in the ordinary sense. It is a sign that we have reached the edge of one layer of understanding and are pressing against another. Every major advance in physics has involved such edges. Classical mechanics worked beautifully until it did not. Electromagnetism worked beautifully until blackbody radiation and atomic structure exposed cracks in the old picture. Newtonian gravity worked beautifully until relativity revealed that time and space themselves were dynamic. In each case, the old theory was not useless. It remained astonishingly good within its range. But the edge where it failed became the birthplace of a deeper view. Planck time may play that same role for the future of physics. It may be one of those markers that tells us exactly where a new understanding is required, and what sort of understanding would that be? Most likely one that changes our view of time more radically than anything before it. That is saying quite a lot because time has already suffered repeated assaults from modern physics. It was once imagined as universal and absolute, the same for all observers everywhere. Relativity overturned that picture and showed that time stretches with motion and gravity. It was once imagined as a smooth background against which matter plays out its motions. Quantum gravity now threatens even that. At the Planck scale, time may not remain continuous, or fundamental, or perhaps even meaningful in the familiar sense. It may be emergent, it may be relational, it may be woven out of structures more basic than temporal sequence. The smallest moment in physics may therefore point toward the possibility that moments themselves are not the deepest furniture of reality. That possibility is difficult to absorb because time is unlike most scientific concepts in one crucial way. We do not merely observe it, we live inside it, we think in sequence, we remember the past, anticipate the future, and feel the present as the moving centre of experience. Even our language is saturated with time. We spend it, lose it, save it, waste it, run out of it, look back on it, and worry about what will happen in it next. To discover that this apparently universal medium may be derivative rather than fundamental is not just a technical revision, it is a challenge to the framework through which we understand existence itself, and yet that challenge is part of what makes the subject so rich. Physics at its best does not only tell us new facts, it changes what counts as obvious. The Earth moves. Simultaneity is relative. Matter is mostly structured emptiness. Particles are not little pellets in the old classical sense. Time may not be basic. Each of these statements begins as an offence against ordinary intuition and ends as a deeper description of reality. There is no guarantee that the current suspicions about Planck time and emergent space-time will survive unchanged into the future, but there is every reason to take seriously the possibility that the world is built on principles less familiar than our inherited intuition suggests. This is where the biggest questions begin to gather. If time is not fundamental, what is? If space-time emerges from something deeper, what sort of thing can give rise to geometry and sequence? Is reality ultimately made of relations, information, quantum states, causal networks, or something for which our current vocabulary is still embarrassingly inadequate? Does the universe begin in time, or does time begin with the universe? Are singularities real physical endpoints, or signs that our concepts have been misapplied? Is the apparent continuity of experience built upon a deeper grain, or is grain itself too simple an image for what lies below? These are not separate puzzles. Planck time pulls them together. One of the biggest questions concerns the meaning of a beginning. Human beings are very fond of beginnings. We like first causes, first moments, first pages, origin stories. The Big Bang naturally attracts this instinct. We want to know what happened first and what came before. But the Planck scale complicates those questions in a profound way. If the earliest universe lies in a regime where time itself is unstable or emergent, then the ordinary demand for an earlier moment may not be physically well posed. That does not settle the matter. There may have been a prior phase, a bounce, or a deeper pre-geometric order. But it does mean that the phrase before the beginning may not be as straightforward as it sounds. Planck time does not answer the question for us. It teaches us how carefully we must ask it. Another big question concerns continuity. Is the universe fundamentally smooth, with Planck time merely marking the boundary of current theory? Or is there truly a minimal temporal grain built into reality? We do not yet know. The temptation to picture time as a series of indivisible ticks is understandable. It offers a clear mental model. But nature has often punished clear mental models when they arrive too early. It may be that time is discrete. It may be that discreteness belongs only to certain observables. It may be that time is emergent and not the kind of thing that is either discrete or continuous at the deepest level. Physics remains open here, and that openness is not weakness. It is a sign that the question is genuinely alive. Then there is the question of explanation itself. Much of science rests on the idea that we can understand complex phenomena by breaking them into simpler parts and studying the laws governing those parts. This has been tremendously successful, but Planck time hints that there may be a level where the usual decomposition strategy runs into trouble, because the concepts doing the decomposing, space, time, location, event, no longer behave independently. The deepest layer may not be composed of simpler pieces in the way ordinary analysis expects. It may require a different kind of explanation, one based more on relations, consistency, emergence, or global structure, than on tiny objects marching through tiny moments. If that is true, then Planck time is not merely a boundary in physics. It is a boundary in our habits of explanation. Black holes sharpen this point beautifully. They show that when gravity becomes extreme, time and information begin to interact in ways that classical intuition cannot manage. The horizon hides. The evaporation radiates. The information puzzle persists. Somewhere in all this, Planck-scale physics must enter. The smallest meaningful interval of time may influence how a black hole evolves, how information is stored, and what counts as a final state. So the biggest questions are not idle philosophy floating above astronomical facts. They are written into the behaviour of the most extreme objects in the universe. The same is true of the early cosmos. A universe younger than a Planck moment is not just a remote curiosity. It is the threshold behind every later structure. Galaxies, stars, planets, chemistry, life, memory, language, all of it unfolds from a cosmos whose earliest regime we still do not fully understand. To study Planck time is, in that sense, to study the hidden foundation of everything that came after. The smallest moment is not peripheral. It may be the deepest clue we have about how reality gets started in the first place. And then there is perhaps the most unsettling question of all. Why do the constants of nature have the values that make the Planck scale what it is? This is not a question physics can yet answer in any final way, but it lingers in the background. Planck time is built from the deep constants associated with relativity, quantum theory and gravity. That gives it an almost architectural status. It is as though the universe has dimensions at which its most basic rules intersect. Why those rules? Why those constants? Why a cosmos in which such a scale even exists? Some physicists hope for a more fundamental theory in which these values are derived necessarily. Others suspect environmental selection in a wider multiverse. Others remain cautious, preferring not to dress ignorance too quickly in grand metaphysical clothing. But the question remains. The smallest moment points beyond itself to the possibility that the laws we know may themselves have a deeper origin. This is one reason Planck time feels oddly philosophical, even when treated with strict scientific discipline. It sits at the point where empirical physics, foundational theory, and metaphysical curiosity begin to overlap. That overlap has to be handled carefully. One should not rush from unknown equations to sweeping declarations about the ultimate nature of reality. But one should not pretend the broader questions are irrelevant either. They arise naturally from the science because the science itself reaches a level where familiar categories become unstable. When the smallest meaningful interval of time calls into question the status of time itself, it is difficult to avoid asking what kind of world could make such a thing possible. Still, there is a danger in speaking too grandly about all this. Topics like Planck time attract big claims, and big claims can be intoxicating. It is tempting to announce that time is definitely an illusion, or that reality is definitely digital, or that space-time definitely emerges from information, or that the universe definitely began in some specific quantum way. Such confidence is usually premature. The honest position is both more modest and more compelling. We know enough to identify the Planck scale as a profound boundary where current theories fail to unify. We know enough to see that black holes, the early universe, and the limits of measurement all point toward the same unresolved domain. We know enough to suspect that time and space-time may not be fundamental in the naive classical sense, but we do not yet know the final theory that makes these suspicions precise. That honesty matters because it preserves the real shape of discovery. Science is not a march from ignorance to slogans, it is a discipline of increasingly careful questions. Planck time gives us one of the most careful and difficult questions in modern physics. It asks what time is when time can no longer be assumed. It asks what changes when events themselves become uncertain. It asks what space-time is when geometry enters the quantum regime. These are not the sorts of questions that yield to impatience, which is perhaps just as well. The universe does not seem inclined to reveal its deepest architecture in a form convenient for creatures who get annoyed waiting for software updates. There is also something quietly humbling in the fact that the biggest questions are opened by the smallest scale. Human beings often imagine significance in terms of size. The grand is important, the tiny is secondary. But physics has spent more than a century dismantling that prejudice. The structure of the atom reshaped civilization. Quantum mechanics transformed philosophy and technology alike. The deep constants of nature reveal themselves not in the broad comfort of everyday scales, but in the places where common sense begins to fail. Planck time continues that tradition. The smallest meaningful interval may hold clues to the most comprehensive picture of reality we are capable of forming. It also changes in a subtle way how one looks at ordinary time. Once you have spent enough attention on Planck time, the second becomes an astonishingly large thing. A second is no longer just a beat on the clock. It is an immense duration compared with the thresholds at which our best theories start to break. Human life unfolds in a broad, comfortable river of time, while beneath that river lies a scale so tiny and so conceptually difficult that the very meaning of duration becomes uncertain. There is something oddly comforting in that. Our days may feel rushed, but from the standpoint of fundamental physics they are extravagantly spacious, and perhaps that helps explain why the subject can feel both unsettling and soothing at once. On the one hand, Planck time reminds us that reality is stranger than it appears. Time may not be what it seems. The universe may be built on structures beyond intuition. Our deepest theories remain incomplete. On the other hand, there is a certain peace in realizing that the familiar world of clocks, conversations, weather, sleep, and memory is not threatened by that strangeness. It is enriched by it. The ordinary remains ordinary, tea still cools, evening still arrives, tiredness still settles into the body with perfect confidence. The mystery underneath does not cancel the surface, it gives it depth. That may be one of the healthiest lessons physics offers. The universe is not diminished by becoming more difficult to understand. It becomes more interesting. The failure of our current ideas at the Planck scale is not an embarrassment to be hidden. It is evidence that discovery is still alive. We have not finished the story. There remains a level at which time, space, gravity, and quantum theory all ask to be understood together. That unfinished work is one of the great privileges of being a thinking species in a lawful universe. We may not know the final answer, but we know enough to know where the answer must be sought. So the smallest moment turns out to carry the largest invitation. It invites us to rethink time, to question continuity, to revisit origins, to confront the deep structure of measurement and causality, and to look at black holes in the early universe not as separate spectacles but as clues to one underlying mystery. Planck time does not give us the final picture. It gives us the doorway to it. A tiny doorway, admittedly, and one with rather unreasonable conceptual demands, but a doorway all the same. And as we ease out of this long quiet thought, it is striking how far the journey has wandered from the phrase smallest unit of time. What sounded at first like a narrow technical detail turned out to touch nearly every foundational question in modern physics. That is often how it goes. The universe hides its largest ideas in the places we least expect them, sometimes in a black hole, sometimes at the beginning of everything, and sometimes in an interval so small that it almost refuses to belong to ordinary thought at all. Yet here we are, still thinking about it in our own much slower corner of time, carried along by seconds that now seem positively generous, with the next question already waiting just beyond the edge of what we know.